Welcome back, cosmic travelers, to the Cosmic Drift Chronicles. If you're new here, you've just stumbled upon humanity's front-row seat to the universe's greatest mysteries. And if you're returning, well, you already know that we don't just observe the cosmos from a distance. We drift through it. We explore it. We descend into its darkest corners and emerge with stories that will change how you see reality itself. Before we begin today's journey, I need you to do something. Look down at that subscribe button. Click it. Join us. Because what we're about to do together requires courage, curiosity, and a crew willing to venture where light itself cannot escape. We're building a community of explorers here, thousands of minds united by wonder, bound by curiosity, connected by our shared desire to understand the incomprehensible, and every journey to the stars is better when we travel together. Today, we're attempting something that would obliterate any physical spacecraft, any probe, any machine we could ever build with current or foreseeable technology. Today, we're going to fall into a black hole. Not just any black hole. We're going to experience what it's really like, from the first gravitational tug millions of miles away, through the swirling chaos of the accretion disk, where temperatures soar to millions of degrees, past the point of no return at the event horizon, where time itself becomes twisted beyond recognition, and finally, into the singularity itself, where physics as we know it breaks down completely, and our journey, and perhaps reality itself, comes to an end. This is a gentle descent into a black hole. There's nothing gentle about it, of course. That's the irony. That's the cosmic joke. But from your perspective, watching from far away at a safe distance, you'd see us slow down, freeze, and fade, as if we were gently suspended in time forever, like a photograph gradually fading in the sun. Meanwhile, from our perspective, we'll be experiencing the most violent, reality-bending, physics-defying journey possible. We'll watch the universe age billions of years in our final moments. We'll feel the very atoms of our bodies stretched like cosmic taffy. We'll witness the end of space and the beginning of impossible geometries. We'll be weaving together over a century of human discovery, from the theoretical whispers of the 18th century, when mathematicians first dared to imagine stars so dense that light couldn't escape them, to the literal photographs of black holes we captured just a few years ago, images that once seemed impossible, that showed us the shadow of infinity itself. We'll explore the brilliant detectives who hunted these invisible monsters across decades of painstaking observation. We'll examine the instruments that finally caught them, telescopes the size of planets, laser interferometers that can measure distances smaller than an atomic nucleus, satellites that map X-rays from the violent feeding frenzies around these cosmic predators. And we'll dive deep into the mind-bending physics that makes them the universe's most extreme laboratories, where Einstein's predictions are tested to their absolute limits, and where the next revolution in physics waits to be discovered. So strap in, adjust your relativistic sensors, check your quantum stabilizers, and prepare for a journey from which there is no return. Let's begin our descent. Before we fall, before we even approach our destination, we need to understand what we're falling into. And that story begins not with telescopes or satellites, not with supercomputers or space missions, but with imagination, with human minds staring at equations and asking, what if? The year is 1783. The place is England, in the closing decades of the Age of Enlightenment. A man named John Michell, an English clergyman and natural philosopher, what we'd call a scientist today, is sitting at his desk doing calculations that would make most people's heads spin. Michell was a polymath, a brilliant mind who contributed to geology, astronomy, and physics. He had already invented the torsion balance that would later be used to measure the gravitational constant. But now, he's working with Newton's laws of gravity and corpuscular theory of light, thinking about gravity and light in ways nobody had before, and he asks himself a strange, almost absurd question. Could there be a star so massive, so incredibly dense, that even light, the fastest thing in the universe, couldn't escape its gravitational pull? This was revolutionary thinking. Radical, almost heretical. At the time, nobody even knew what light really was. Was it a particle? A wave? Some kind of mysterious fluid that filled space? The debate raged. But Michel calculated that if you had enough mass concentrated in one place, if you could squeeze enough matter into a small enough volume, the escape velocity, the speed needed to break free from that object's gravitational grip, could exceed the speed of light itself. He called these hypothetical objects dark stars. Stars that would be completely invisible because no light could ever climb out of their gravitational wells. Think about how extraordinary this is. In 1783, the United States had just won its independence. The French Revolution was 6 years away. Steam engines were cutting-edge technology. And here was a clergyman imagining objects so extreme that they wouldn't be confirmed to exist for nearly 200 years. 13 years later, in 1796, the brilliant French mathematician Pierre-Simon Laplace, one of the founding fathers of mathematical physics, the man who would systemize celestial mechanics and probability theory, independently came to the same conclusion. Laplace was working through the implications of Newtonian gravity, running thought experiments about escape velocity, and realized that sufficiently massive compact objects could trap light. He even published this idea in the first edition of his monumental work, Exposition du Système du Monde, Exposition of the System of the World. But here's the thing. The idea was too strange, too far ahead of its time, too disconnected from anything that could be observed or tested with 18th century technology. Without any way to detect such objects, without any framework for understanding how they might form, without any connection to observable phenomena, the concept of dark stars faded into obscurity for over a century. Laplace removed the discussion from later editions of his book. The idea was forgotten, buried in old journals and dusty libraries, waiting for the right moment to return. That moment came with Albert Einstein. Fast forward to 1915. The world is consumed by the Great War. Europe is tearing itself apart. And in Berlin, Albert Einstein, already famous for his special theory of relativity and his explanation of the photoelectric effect, publishes what will become his masterpiece, the general theory of relativity. This theory completely revolutionized our understanding of gravity. In Einstein's universe, gravity isn't a force pulling objects together across empty space, as Newton had described it. No, gravity is something far stranger, far more fundamental. Gravity is the curvature of space-time itself. Mass and energy don't just exist in space, they bend space. They warp it. They create curves and valleys in the fabric of reality. And other objects, other masses, don't feel a force pulling them. They simply follow the straightest possible paths through this curved geometry. A planet orbiting a star isn't being pulled by an invisible force. It's following a curved path through space-time that's been warped by the star's mass. It's like placing a bowling ball on a trampoline. The bowling ball creates a depression, a curve in the fabric. Now roll a marble nearby, and it will curve toward the bowling ball, not because the bowling ball is pulling it, but because the marble is following the curved surface. Einstein's equations were beautiful. They were elegant. They unified space and time into a single four-dimensional fabric. They explained the orbit of Mercury, which had puzzled astronomers for decades. They predicted that light would bend around the sun, which was confirmed during a solar eclipse in 1919, making Einstein an international celebrity overnight. But they were also incredibly difficult to solve. Einstein's field equations are a set of 10 interrelated differential equations, and finding exact solutions, mathematical descriptions of specific spacetime geometries, was extraordinarily challenging. Most people assumed that only approximate solutions, numerical solutions, would ever be found. That you'd need to make simplifying assumptions and use computers, which didn't exist yet, to get answers. But in 1916, while serving on the Russian front during World War I, in the trenches between artillery barrages, a German physicist named Karl Schwarzschild did the impossible. Schwarzschild was already an accomplished astronomer and physicist. He had made important contributions to stellar physics and spectroscopy. But here, in the horror of the Eastern Front, suffering from a painful autoimmune disease that would kill him within months, he found an exact solution to Einstein's field equations. His solution described the geometry of spacetime around a perfectly spherical, non-rotating mass. It was exact, it was beautiful, and it was strange. Hidden in Schwarzschild's mathematics was something extraordinary, something that even Schwarzschild himself didn't fully appreciate. A radius at which spacetime curves so severely, so extremely, that it essentially closes off from the rest of the universe. Cross that boundary, and you can never return. Not because you lack fuel or energy, but because the geometry of spacetime itself makes return impossible. This boundary, the point of no return, became known as the Schwarzschild radius, and it defines the event horizon of every non-rotating black hole. For any object, you can calculate its Schwarzschild radius. For the Sun, it's about 3 kilometers. That means if you could somehow compress the entire Sun down to a sphere less than 3 kilometers in radius, it would become a black hole. For Earth, the Schwarzschild radius is about 9 millimeters. For you, it's about 10 to the power of negative 25 meters, far, far smaller than an atomic nucleus. Obviously, these compressions don't happen in nature for objects like the Sun or Earth. But Schwarzschild's solution showed that if such compression did happen, a black hole would inevitably form. Interestingly, Einstein himself didn't believe these objects could actually exist in nature. They were mathematical curiosities, he thought, artifacts of idealized equations, results that appeared when you made unrealistic assumptions like perfect spherical symmetry. In the messy reality of our universe, with rotation and irregularities and disturbances, surely these extreme solutions wouldn't occur. Einstein even published a paper in 1939 arguing that black holes couldn't form because matter would never cooperate enough to collapse to such extreme densities. But that same year, Robert Oppenheimer, yes, the same Oppenheimer who would later lead the Manhattan Project and become known as the father of the atomic bomb, teamed up with his student Hartland Snyder to publish something groundbreaking. They showed, through careful calculation, that when a massive enough star exhausts its nuclear fuel, nothing could stop it from collapsing into one of these Schwarzschild objects. They worked through the physics of stellar collapse step by step. When a star runs out of fuel, it can no longer support itself against gravity. For massive enough stars, the collapse would continue past the neutron star stage, past any possible resistance from quantum pressure, past any conceivable stopping point. The math was clear. The physics was inescapable. Black holes weren't just possible. They were inevitable. This was a stunning conclusion. It meant that the universe naturally creates these objects. They're not artificial constructs or mathematical fantasies. They're the end state of massive stars, as natural and inevitable as birth and death. Still, nobody called them black holes yet. The terminology was awkward. Scientists used terms like frozen stars, because time dilation makes infalling matter appear to freeze at the boundary, or collapsed stars, or Schwarzschild singularities. Names that tried to capture the bizarre nature of these objects without fully embracing their strangeness. The term frozen star was particularly popular in the Soviet Union, where physicist Yakov Zeldovich and his colleagues were making important contributions to understanding stellar collapse. Then came 1967. Physicist John Wheeler, a towering figure in 20th century physics, Richard Feynman's PhD advisor, the man who popularized the term wormhole and contributed to quantum mechanics, nuclear physics, and relativity, was giving a lecture. During the question and answer session, someone in the audience suggested the term black hole, and Wheeler seized on it immediately. He started using it in his talks and papers. The name was perfect. Simple, evocative, memorable. The name captured something essential about these objects. They weren't just stars that had gone dark. They were holes in the fabric of reality itself, regions where the normal rules broke down, where space-time had a hole punched through it, where matter and energy could fall in but never return. By the late 1960s, black holes had transformed from mathematical fantasy to serious scientific prediction. Theoretical physics had done its job. The equations were solved. The predictions were clear. Now came the hard part: finding them. How do you find something that emits no light? How do you detect the invisible? How do you photograph something that, by definition, cannot be photographed? This was the challenge facing astronomers in the 1960s and 1970s. They had theoretical predictions. They had mathematical models. They had good reasons to believe black holes should exist. But science requires evidence, observation, detection. The answer, it turned out, was to look for the chaos around them. To study not the black holes themselves, but their effects on nearby matter and light. In 1964, a rocket-borne X-ray detector launched from New Mexico detected a powerful source of X-rays coming from the constellation Cygnus, about 6,000 light-years away. They called it Cygnus X-1, the first X-ray source discovered in Cygnus. At first, nobody knew what it was. X-ray astronomy was brand new. The Earth's atmosphere blocks X-rays, so you need rockets or satellites to detect cosmic X-rays. Every detection was a mystery waiting to be solved. As observations improved through the 1960s, a picture emerged. There was a blue supergiant star, a massive, visible star with a well-understood spectrum, and it was orbiting something invisible. The star's motion revealed that it was gravitationally bound to a companion. They could measure the orbital period, 5.6 days, the orbital radius, and from that, they could calculate the mass of the invisible companion. And that mass was enormous. At least 10 times the mass of the Sun, packed into a region that couldn't be seen at any wavelength. But the real smoking gun was the X-rays. As gas from the blue supergiant spiraled toward the invisible companion, it heated up to millions of degrees through friction and compression, emitting intense X-rays before vanishing forever into nothing, into the invisible companion. By 1971, scientists had calculated and recalculated. They'd ruled out other possibilities. The invisible companion was too massive to be a neutron star. Neutron stars max out at about 2 to 3 solar masses. It wasn't a white dwarf. It wasn't a dim star. The evidence pointed to one conclusion. Cygnus X-1 was a black hole. It became the first widely accepted black hole candidate. But not everyone was convinced. Stephen Hawking, already establishing himself as one of the world's leading theoretical physicists, despite the motor neuron disease that was gradually paralyzing his body, was skeptical. This seems odd. Hawking had done groundbreaking work on black holes. He'd proven important theorems about their properties. Why would he doubt their existence? In 1975, Hawking made a bet with fellow physicist Kip Thorne, who was convinced Cygnus X-1 was a black hole. Hawking bet against it. He wagered a subscription to Penthouse magazine, which Thorne would receive if it was a black hole, against a subscription to Private Eye, a satirical magazine, which Hawking would receive if it wasn't. Why would Hawking bet against his own field of research? As he explained, it was insurance. If black holes didn't exist, if his life's work was based on mathematical fantasies, at least he'd win a magazine subscription. A small consolation for a collapsed theoretical framework. But the evidence kept mounting. More observations. Better data. Higher precision measurements. The mass estimate for the invisible companion kept coming back at 15 to 16 solar masses. Way too heavy for anything but a black hole. In 1990, Hawking conceded the bet. He broke into Thorne's office at Caltech and signed the bet concession document, admitting that Cygnus X-1 was indeed a black hole. Thorne never actually took out the Penthouse subscription, but the concession stood. Cygnus X-1 was real. But Cygnus X-1 was just the beginning, just the first of many discoveries. Throughout the 1970s and 1980s, astronomers began finding these X-ray binary systems throughout our galaxy. Systems where a black hole was actively feeding on a companion star, pulling gas away through gravitational tidal forces, heating it to extreme temperatures, and revealing its presence through the death screams of infalling matter. Each discovery added another data point, another confirmation that these monsters were out there, lurking in the darkness, invisible except for the violence they inflicted on their surroundings. X-ray satellites like Uhuru, launched in 1970, Rosat, Chandra, and XMM Newton catalogued dozens, then hundreds of X-ray sources. Many turned out to be neutron stars, but a significant fraction, those with higher masses and specific characteristics, were black holes. Then came an even bigger revelation, one that would reshape our understanding of galaxies themselves. For decades, astronomers had noticed something strange happening at the center of our Milky Way galaxy. Stars near the galactic center were moving fast. Really fast. Absurdly fast. They were whipping around in tight elliptical orbits, sometimes reaching speeds of thousands of kilometers per second, as if they were orbiting something incredibly massive packed into a tiny region. But when they looked at the center with optical telescopes, they saw nothing. No bright object. No obvious source of gravity. Just stars whizzing around an empty point in space. Two teams, working independently, decided to solve this mystery through brute force observation. One team was led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics in Germany. The other was led by Andrea Ghez at UCLA. Their approach was simple in concept, but extraordinarily difficult in execution. Track individual stars orbiting the galactic center over years and decades, map their orbits precisely, and calculate what they must be orbiting. This required cutting-edge technology. The center of our galaxy is 27,000 light-years away. It's obscured by dust that blocks visible light. And the stars they needed to track move significantly only over years of observation, requiring long-term dedication and consistency. They used infrared telescopes. Infrared light penetrates dust better than visible light. They used adaptive optics to compensate for atmospheric distortion, creating images nearly as sharp as space telescopes. And they were patient. Year after year. Observation after observation. Painstakingly tracking individual stars. One star in particular, called S2, or S0-2 in Gez's catalogue, became the Rosetta Stone. S2 has an elliptical orbit with a period of about 16 years. At its closest approach, it comes within just 17 light-hours of the galactic center, about 4 times the distance from the Sun to Neptune, and reaches speeds up to 3% of the speed of light. By tracking S2 and other stars over complete orbits, the teams could apply Kepler's laws of orbital motion and calculate the mass of whatever they were orbiting. And the conclusion was inescapable. At the center of our galaxy, something with a mass of roughly 4 million suns was occupying a region smaller than our solar system. There's only one thing that massive and that compact: a supermassive black hole. They called it Sagittarius A*, pronounced Sagittarius A star, named after the radio source that had been detected there decades earlier. Our galaxy's own supermassive black hole. And we've been orbiting it for the Sun's entire 4.6 billion-year lifetime, making the circuit once every 230 million years or so. The work was monumental. It spanned decades. It required technological innovation, persistence, and precision. And in 2020, Reinhard Genzel and Andrea Ghez were awarded the Nobel Prize in Physics for proving that Sagittarius A* exists. They shared the prize with Roger Penrose, who had proven that black holes are a robust prediction of general relativity. It was a triumph of observational astronomy. But even with all this evidence, the X-rays from accreting black holes, the orbital mechanics proving supermassive black holes, the gravitational signatures, the theoretical predictions, scientists wanted more. They wanted to see a black hole, to photograph it, to capture the shadow of the event horizon itself. Which brings us to April 10th, 2019, a date that will be remembered in the history of astronomy. The Event Horizon Telescope isn't actually a single telescope. It's not even a single observatory. It's a network of 8 radio telescopes scattered across the globe, from Hawaii to Arizona to Chile to Spain to Antarctica, all synchronized to work together as one Earth-sized virtual telescope through a technique called very long baseline interferometry. The basic idea is this: when 2 or more radio telescopes observe the same object simultaneously, you can combine their signals and create an effective resolution equivalent to a telescope the size of the separation between them. The farther apart the telescopes, the higher the resolution. By coordinating telescopes across the entire planet, the Event Horizon Telescope achieved an angular resolution of about 20 microarc seconds, fine enough to read a newspaper in New York from a cafe in Paris, or to photograph a black hole 55 million light-years away. The target was M87*, the supermassive black hole at the center of the giant elliptical galaxy Messier 87. Why M87*, and not our own Sagittarius A*? Because even though M87* is 2,000 times farther away, it's also 1,500 times more massive, making its apparent size in the sky larger. And crucially, M87* is more stable. Matter orbits it over days and weeks rather than minutes, making it easier to photograph. The technical challenges were immense. The observations happened over several nights in April 2017, with all 8 telescopes pointing at M87* simultaneously, collecting data from the radio emissions around the black hole. The data collected was so massive, about 5 petabytes, equivalent to about 5,000 years of MP3 audio, that it couldn't be transmitted over the internet. It literally had to be physically flown on hard drives to central processing facilities in Massachusetts and Germany, where supercomputers began the painstaking process of combining the signals. Teams of scientists from around the world worked for 2 years processing the data. One crucial contributor was Katie Bauman, then a graduate student at MIT, who developed important imaging algorithms that helped convert the raw interferometry data into an actual image. Her algorithms had to solve an incredibly difficult problem. How do you create an image when you have data from only 8 points on Earth, leaving enormous gaps in your coverage? The answer involved sophisticated techniques from signal processing, using mathematical tricks to fill in the gaps, testing thousands of different image reconstructions, and looking for features that appeared consistently regardless of the reconstruction method used. And then, on April 10, 2019, the Event Horizon Telescope team revealed their results in simultaneous press conferences around the world. The world saw it, a glowing ring of light, orange and yellow in the false color image, surrounding a dark shadow. The shadow of a black hole's event horizon, backlit by the blazing accretion disk of superheated matter spiraling around it. M87 was revealed. The image showed exactly what Einstein's equations predicted. The shadow was circular, as expected for a black hole viewed nearly face-on. The ring was asymmetric, brighter on one side, because of Doppler boosting. Matter on one side of the disk is moving toward us at nearly the speed of light, amplifying its brightness, while matter on the other side is moving away. The black hole in that image has a mass of 6.5 billion suns. To put that in perspective, if you replaced our Sun with M87*, its event horizon would extend past the orbit of Pluto. The entire solar system would fit comfortably inside it, with room to spare. And that ring of light? That's matter being destroyed. Gas heated to billions of degrees, shining in its final moments before crossing the event horizon and vanishing forever. The image wasn't just beautiful. It was scientific validation. The size of the shadow matched predictions from general relativity to within 10%. The mass calculated from the shadow matched other independent measurements. Everything checked out. For the first time in human history, we weren't just inferring that black holes exist, we were looking at one. But the Event Horizon Telescope team wasn't done. In 2022, they released their second black hole image, this time of Sagittarius A*, our own galaxy's central black hole. This image was harder to capture. Sagittarius A* is smaller and closer, which is normally an advantage, but matter orbits it much more quickly, completing circuits in minutes rather than days. The black hole itself appears to flicker on timescales of minutes, like trying to photograph a fidgeting child versus a patient adult. The team had to develop new techniques, effectively taking thousands of snapshots and averaging them to create a stable image. But they succeeded, and the image shows the same structure, a glowing ring surrounding a dark shadow. We've now photographed 2 black holes. We've seen their shadows. We've measured their masses and sizes. We've confirmed that Einstein was right, that Schwarzschild's solution describes reality, that Oppenheimer's calculations predicted what actually happens. These images weren't just scientific achievements. They were proof that the impossible mathematics of the early 20th century, the wild predictions that Einstein himself doubted, the theoretical musings that seemed like science fiction, they were all real. We had found the invisible. We had photographed the unphotographable. And now, it was time to understand what we'd found. Now that we know black holes exist, now that we've seen them and measured them and confirmed their properties, we need to appreciate their extraordinary diversity. Because not all black holes are created equal. They come in wildly different sizes, different ages, different personalities, if you can call them that. The universe, it turns out, is remarkably creative in how it makes these objects. Let's start with the most common type, the ones we understand best, stellar mass black holes. These are formed when massive stars, at least 20 to 25 times the mass of our Sun, sometimes much more, reach the end of their lives. Stars are engines that fight gravity. Nuclear fusion in the core generates heat and pressure that pushes outward, counteracting the star's tendency to collapse under its own weight. It's a delicate balance that can last millions or billions of years. But eventually, every star runs out of fuel. When a massive star exhausts its nuclear fuel, when its fused elements all the way up to iron in its core and can't fuse anymore, because iron fusion consumes energy rather than releasing it, the core has nothing left to support it. What happens next is violent and fast. The core collapses in less than a second. Not minutes. Not hours. Less than 1 second. The collapse is catastrophic, releasing more energy than the Sun will produce over its entire 10 billion-year lifetime. This energy blows the outer layers of the star away in a supernova explosion, one of the most energetic events in the universe. But the core? If the core is massive enough, nothing can stop the collapse. First, electron degeneracy pressure tries to stop it, the quantum mechanical principle that prevents electrons from occupying the same state. This can create a white dwarf for smaller cores. But for massive enough cores, gravity overwhelms even this. Next, neutron degeneracy pressure tries to stop it, the even stronger quantum pressure that prevents neutrons from being compressed too close together. This can create a neutron star, an object about 1.4 to maybe 3 solar masses compressed into a sphere about 20 kilometers across, where a teaspoon of matter weighs 1 billion tons. But if the core is massive enough, somewhere above 2 to 3 solar masses, the exact limit is still debated. Even neutron degeneracy pressure fails. Gravity wins. The collapse continues. Space-time warps more and more severely. An event horizon forms. And you have a black hole. These stellar mass black holes typically range from about 3 solar masses, the theoretical minimum, to several dozen solar masses, though recent gravitational wave detections have found some up to 100 solar masses or more, which is puzzling because theoretical models didn't predict stars could form black holes that massive. The smallest confirmed black hole we've found is about 3.8 solar masses, right near the theoretical minimum. There's probably a gap between the most massive neutron stars, around 2 to 3 solar masses, and the lightest black holes, around 3 to 5 solar masses, though we're still searching for objects in this gap. Our galaxy probably contains hundreds of millions of these stellar mass black holes, the remnants of massive stars that have died over the Milky Way's 13 billion-year history. Most are completely isolated, invisible, detectable only if they happen to pass in front of a background star and cause gravitational microlensing, a brief brightening as the black hole's gravity focuses the star's light. Then we have the titans, the monarchs of the cosmic menagerie, supermassive black holes. These monsters contain millions to billions of solar masses and lurk at the centers of most large galaxies, like spiders at the centers of their webs. And by most large galaxies, I mean virtually all of them. Nearly every galaxy we've studied in detail that's massive enough to have a significant bulge has a supermassive black hole at its center. Supermassive black holes aren't formed from stellar collapse. They're way too big for that. A stellar mass black hole of 30 solar masses would have to consume matter equivalent to millions of stars to become a supermassive black hole. And there simply hasn't been enough time in the history of the universe for that to happen through gradual feeding alone. So how did they form? This is one of astronomy's ongoing mysteries. Several theories exist. Some scientists believe they formed through the direct collapse of massive gas clouds in the early universe. In the first billion years after the Big Bang, before the first stars had manufactured much heavy elements, gas clouds might have been able to collapse directly into massive black holes without fragmenting into stars first. Others think they grew through the merger of many smaller black holes over cosmic time, or through a combination of mergers and sustained feeding on gas funneled to galactic centers. What's shocking, genuinely shocking to astronomers, is how early some of these supermassive black holes appeared. We've detected them in galaxies that existed less than 1 billion years after the Big Bang, less than 7% of the current age of the universe. Some of these early supermassive black holes are already 1 billion solar masses. How did they grow so massive so quickly? The universe was young. There wasn't much time for gradual growth. This is called the supermassive black hole formation problem, and it's an active area of research. Proposed solutions include super-Eddington accretion, feeding faster than theoretical limits should allow, exotic formation mechanisms, or populations of seed black holes that we haven't detected yet. The relationship between galaxies and their central black holes is intimate and mysterious. In 2000, astronomers discovered what's now called the M-sigma relation. The mass of a galaxy's supermassive black hole is directly correlated with the velocity dispersion of stars in the galaxy's bulge, a measure of the bulge's mass. This is weird. The black hole is tiny compared to the galaxy. Sagittarius A** contains only about 0.001% of the Milky Way's total mass. How does such a tiny fraction of the galaxy's mass know to be correlated with the much larger galactic bulge? The implication is that somehow, across billions of years, galaxies and their black holes co-evolved, shaping each other through a feedback loop we're still trying to understand. The black hole's jets and radiation regulate star formation in the galaxy. The galaxy funnels gas toward the black hole, feeding it. They grow together, maintaining this tight relationship. Between stellar mass black holes and supermassive black holes, there's a missing link that we've only recently begun to find. Intermediate mass black holes, ranging from hundreds to hundreds of thousands of solar masses. These are theoretically predicted, but observationally rare. They should exist as a bridge between the two main populations. And in recent years, we've started confirming them through multiple methods. Gravitational wave detections have found merging black holes in the intermediate mass range, too massive to be straightforward stellar remnants. Ultraluminous X-ray sources, objects too bright to be stellar mass black holes, but in the wrong locations to be galactic center supermassive black holes, might be intermediate mass black holes feeding actively. Dense star clusters might harbor intermediate mass black holes at their centers, formed through repeated mergers of stellar mass black holes. These intermediate mass black holes are crucial to understanding how supermassive black holes formed. They might be the seeds that grew into the monsters we see today, or they might represent an ongoing process of black hole growth through merger hierarchies. And then there are the exotic possibilities, the theoretical predictions that might exist but remain unconfirmed. Primordial black holes may have formed in the first fraction of a second after the Big Bang, created by extreme density fluctuations in the infant universe before the first atoms even formed. These wouldn't form from stellar collapse. They'd form directly from the compression of space itself during the violent first moments of cosmic inflation. If they exist, they could range from incredibly tiny, far smaller than an atomic nucleus, to stellar mass or even larger. Some scientists speculate they might even make up part or all of the mysterious dark matter that dominates the universe's mass, but doesn't emit light. Small primordial black holes could be scattered throughout the cosmos, invisible, contributing to the gravitational effects we attribute to dark matter. Recent studies have put constraints on this idea, but it hasn't been ruled out entirely. Micro-black holes are hypothetical tiny black holes that could theoretically form from ultra-high-energy particle collisions. There was brief concern when the Large Hadron Collider was being built that it might create micro-black holes, but even if it could, which is doubtful, they'd evaporate essentially instantly through Hawking radiation, which we'll discuss in detail later, posing no danger whatsoever. Let's talk about some record holders, because black holes love extremes. Ton 618 is one of the most massive black holes ever discovered, approximately 66 billion solar masses. It's so massive that if it replaced our Sun, its event horizon would extend well past the orbit of Pluto, past the Kuiper belt, reaching nearly to the inner edge of the Oort cloud. The sphere encompassed by its event horizon could contain dozens of solar systems. Ton 618 is also a quasar, an actively feeding supermassive black hole, so bright it outshines its entire host galaxy. We can see it from 10 billion light-years away, which means we're seeing it as it was 10 billion years ago, when the universe was less than a quarter of its current age. At the other extreme, the smallest confirmed black hole is about 3.8 solar masses, near the theoretical minimum. Below about 3 solar masses, the physics of degeneracy pressure can create a neutron star instead of a black hole. This creates a natural minimum mass for black holes, though the exact value depends on complex nuclear physics we don't fully understand. The closest known black hole to Earth was recently discovered, and is called Gaia BH1, at approximately 1,560 light-years away. That might sound far, and it is by human standards, but in galactic terms, it's practically next door. It's about 100 times closer than Cygnus X1. It's a stellar mass black hole, about 10 solar masses, orbiting a Sun-like star, and it was discovered through careful analysis of stellar motions detected by the Gaia Space Telescope. There's likely an even closer black hole that we haven't found yet, possibly within a few hundred light-years. These isolated black holes are extremely difficult to detect unless they happen to have a companion star or pass in front of a background star. Black holes also come in different states or modes based on what they're doing, based on their feeding behavior. A quasar is a supermassive black hole actively gorging itself on enormous quantities of matter, shining brighter than hundreds of billions of stars combined. The brightest quasars can outshine their entire host galaxies by factors of 100 or more. The name quasar is short for quasi-stellar radio source. When they were first discovered in the 1960s, they looked like stars in optical images, but emitted powerful radio waves, and nobody knew what they were. It took years to figure out they were extremely distant, extremely luminous galactic centers powered by supermassive black holes. Some quasars consume the equivalent of several hundred Earths every minute. Thousands of tons of matter per second, all heated to millions of degrees, all shining with the combined fury of hundreds of billions of stars before crossing the event horizon and vanishing. These feeding frenzies create what we call active galactic nuclei, AGN. Galaxy centers so bright they outshine everything else. There are different types depending on the viewing angle and feeding rate. Quasars, blazars, Seyfert galaxies, radio galaxies. All are powered by supermassive black holes actively feeding. But not all black holes are eating. Many, probably most, are quiet, dormant, waiting in the darkness. Sagittarius A** is actually relatively quiet compared to many galactic centers. It's feeding at a very low rate, consuming only about 1 Earth mass of material every few thousand years. It's nearly starving. This is good for us. If Sagittarius A* were actively feeding like a quasar, the radiation would likely sterilize much of the galaxy, making life far more difficult or impossible. Some supermassive black holes alternate between active and quiet states as their food supply varies. A galaxy merger might funnel enormous amounts of gas toward the central black hole, triggering a quasar phase that lasts millions of years. Then the food runs out, and the black hole goes quiet again. The universe, it turns out, is full of these gravitational monsters at every scale. Stellar mass black holes likely number in the hundreds of millions, just in our galaxy alone, perhaps 1 billion or more scattered through the Milky Way. Every spiral arm, every star cluster, every region where massive stars have lived and died likely harbors these remnants. And nearly every large galaxy has a supermassive black hole at its heart, a gravitational anchor that has been there for billions of years, that has shaped the galaxy's evolution, that will outlast every star in the galaxy by incomprehensible timescales. We're not alone in the cosmos. We're surrounded by them. They're part of the cosmic ecosystem, as natural as stars and planets, as inevitable as gravity itself. So what exactly is a black hole? What are we actually talking about when we describe these objects? This is where we need to get precise, where we need to dive into the geometry of space-time itself, and understand what makes black holes so fundamentally different from everything else in the universe. At the center of every black hole, according to general relativity, lies the singularity, a point of infinite density where all the black hole's mass is concentrated into zero volume. Think about that for a moment. Not just very dense, not just compressed beyond imagination. Infinite density, zero volume. All the mass of millions or billions of suns compressed into a mathematical point with no size at all. At least, that's what the math says. That's what you get when you solve Einstein's equations and follow the collapse all the way to its conclusion. In reality, we don't actually know what happens at the singularity because our physics completely breaks down there. General relativity predicts its own failure. The equations return infinities, which is physics speak for I don't know what's happening anymore. Quantum mechanics should become important at such extreme densities and small scales, but we don't have a working theory of quantum gravity that can describe what happens. The singularity is where our understanding ends, where the known laws of physics meet their limits, where we confront our ignorance most directly. The singularity might not actually be a point. It might be a region where space-time becomes quantized, granular, foamy at the Planck scale, about 10 to the power of negative 35 meters. It might be a region where new physics we haven't discovered yet takes over. Or it might really be a true mathematical singularity, a place where reality breaks. We don't know. And more frustratingly, we might never know, because surrounding the singularity is the event horizon, the point of no return, the boundary that defines the black hole. The Schwarzschild radius defines this boundary. For a non-rotating black hole, it's simple to calculate. Rs equals 2gm/c², where g is the gravitational constant, m is the mass, and c is the speed of light. For our Sun, about 3 kilometers. For Earth, about 9 millimeters. For Sagittarius A*, about 12 million kilometers, roughly 17 times the Sun's radius. For M87*, about 19 billion kilometers, larger than our entire solar system. Cross this boundary, and escape becomes impossible. Not difficult. Not unlikely. Not, you'd need a really powerful rocket. Physically, geometrically, mathematically impossible. Here's why. Inside the event horizon, the roles of space and time swap. Outside the horizon, you can choose to move left or right, forward or backward, but you can't choose to move backward in time. Time only goes forward. Inside the horizon, the singularity is no longer a location in space. It's a moment in your future. Just as you can't avoid tomorrow, you can't avoid the singularity. All paths lead there. Every direction you try to move takes you closer. It's not a place you fall toward. It's a time you fall toward. This is genuinely one of the strangest predictions of general relativity. Inside the event horizon, trying to escape is like trying to escape tomorrow. You can struggle all you want, fire your rocket engines at maximum, but you're just determining how you reach the singularity, not whether you reach it. But here's what's fascinating and deeply weird. The experience of crossing the event horizon is completely different depending on who's watching, depending on your reference frame. From an outside observer's perspective, say, you're watching a friend fall into a black hole from a safe distance. Time dilation becomes extreme as they approach the horizon. General relativity predicts that clocks run slower in stronger gravitational fields. Near the event horizon, this effect becomes infinite. As your friend approaches, you see them slow down. Their movements become sluggish, like a video playing in slow motion. Their clock ticks slower and slower compared to yours. Eventually, they appear to freeze at the horizon, their image becoming permanently imprinted on the event horizon, like a photograph slowly fading. Their light becomes increasingly redshifted, stretched to longer wavelengths, dimming from visible light to infrared to radio waves to nothing. You never actually see them cross. From your perspective, they approach the horizon asymptotically, getting closer and closer, but never quite reaching it, taking literally infinite time to cross as measured by your clock. Meanwhile, from your friend's perspective, something completely different happens. They experience nothing special at the event horizon. No barrier, no wall, no membrane. They cross it normally, smoothly, without any indication that they've passed the point of no return. Their clock ticks normally from their perspective. If they look back at you, they'd see you accelerating, the universe appearing to speed up above them. Time dilation works both ways. From their perspective, you're in a weaker gravitational field, so your clock runs faster compared to theirs. This is the nature of relativity. Two perspectives, both completely valid, both objectively true in their own reference frames, yet describing completely different experiences. One observer sees their friend freeze at the horizon. The other crosses smoothly and continues falling. This isn't a contradiction. It's a feature of how space-time works, how simultaneity and time aren't absolute, but depend on your motion and position in a gravitational field. Once past the event horizon, once your friend has crossed that boundary, tidal forces begin to dominate their experience. Tidal forces arise because gravity decreases with distance. Your feet, closer to the singularity, feel stronger gravity than your head. In normal circumstances, standing on Earth, this difference is negligible. But near a black hole, the difference becomes extreme. This is spaghettification, one of physics' most whimsically named phenomena, describing an absolutely horrifying death. The gravitational gradient across your body becomes so extreme that your feet, or whatever part is closest to the singularity, are pulled thousands or millions of times harder than your head. You're stretched vertically, elongated like taffy being pulled, while simultaneously being compressed horizontally as geodesics, paths through spacetime, converge toward the singularity. You're literally turned into a long, thin stream of atoms, like cosmic spaghetti. For stellar mass black holes, this happens before you even reach the event horizon. The tidal forces at the horizon are so strong that your body would be torn apart atom by atom while still outside the black hole. You'd die long before crossing the point of no return. But for supermassive black holes, the tidal gradient is much gentler because the horizon is so much farther from the singularity. The tidal force at a given radius depends on m/r⁻3, so more massive black holes have weaker tidal forces at their horizons. For a supermassive black hole, like Sagittarius A** or M87**, you could cross the event horizon completely intact, alive, conscious, experiencing nothing unusual. You'd have time, minutes, perhaps, to contemplate your fate as you fall through a region where physics as we know it still applies, where you're still a coherent human being. Spaghettification wouldn't begin until you're much closer to the singularity, when the tidal gradient becomes strong even by supermassive black hole standards. This is why we chose a supermassive black hole for our thought experiment. We want to survive long enough to experience the journey, to cross the horizon consciously, and see what lies beyond. Now, I've been describing non-rotating black holes, Schwarzschild black holes. But most black holes in nature don't just sit there. They rotate. And rotation changes everything, adds layers of complexity and weirdness. A rotating black hole is described by the Kerr solution to Einstein's equations, discovered by Roy Kerr in 1963. This solution is more complicated than Schwarzschild's, but describes the real black holes we find in nature. A rotating black hole drags spacetime itself around with it, in an effect called frame dragging, or the Lentz-Thirring effect. Imagine spacetime as a fluid. A massive rotating object stirs this fluid, creating a current. Near the black hole, space itself is being pulled in the direction of rotation. This isn't a metaphor. Space-time itself is rotating. This creates the ergosphere, a region outside the event horizon where it's impossible to stand still relative to distant stars. Space-time itself is moving, and you're carried along with it like a swimmer caught in a current. The ergosphere is shaped like a flattened ellipsoid, widest at the equator and touching the event horizon at the poles. Inside the ergosphere, you can still escape. You're outside the event horizon, but you must be moving in the direction of the black hole's rotation. The British physicist Roger Penrose realized you could theoretically extract energy from a rotating black hole using the ergosphere. The process, now called the Penrose process, works like this. You send a particle into the ergosphere. The particle splits into two pieces. One piece falls into the black hole with negative energy, as measured from infinity, while the other escapes with more energy than the original particle. This doesn't violate conservation of energy because you're stealing rotational energy from the black hole itself, slowing down its rotation. The black hole loses mass and angular momentum in the process. It's wildly impractical with particles, but some astrophysicists think the jets launched by black holes might be powered by a variant of the Penrose process, extracting rotational energy from spinning black holes through electromagnetic processes. Rotating black holes also have an innermost stable circular orbit, ISCO, the closest you can orbit without falling in. Outside the ISCO, stable orbits exist. Inside it, there are no stable orbits. You either escape or fall, no middle ground. For a non-rotating black hole, the ISCO is at 3 times the Schwarzschild radius. For a maximally rotating black hole, it's much closer, just 1.5 times the Schwarzschild radius at the equator. Matter in an accretion disk orbits at the ISCO, heated by friction, radiating energy. Then it crosses the ISCO and plunges toward the event horizon on unstable orbits, becoming invisible in the final moments before crossing. At 1.5 times the Schwarzschild radius lies the photon sphere, a region where spacetime is so warped that light itself can orbit the black hole. This is exactly what it sounds like, photons moving in circles around the black hole, trapped in orbits by the curvature of spacetime. If you could somehow position yourself at the photon sphere and look to the side, you'd see the back of your own head as photons circle around the black hole and return to you. You'd see multiple images of yourself, infinitely regressing as light loops around again and again. The photon sphere is unstable, though. The slightest perturbation sends photons either falling in or escaping. But it's a critical concept because it determines how the black hole's shadow appears. Light from behind the black hole that passes through the photon sphere region can loop around and escape, creating the bright ring we see in event horizon telescope images. Remarkably, despite all this complexity, ergospheres, frame dragging, photon spheres, innermost stable circular orbits, black holes are defined by only 3 properties according to what's called the no-hair theorem. The theorem, cheekily named, states that black holes have no distinguishing features, no hair. Once matter crosses the event horizon, all information about its composition vanishes. The only things that remain are 1. Mass, how much stuff fell in. 2. Spin, how much angular momentum it has. 3. Electric charge, the net electric charge, that's it. It doesn't matter if the black hole formed from hydrogen or iron, from matter or antimatter, from a star or a direct collapse. It doesn't matter what fell in last week or 1 billion years ago. All that information is lost. Only mass, spin, and charge remain. This is profoundly strange. It means black holes are the simplest macroscopic objects in the universe. A star has composition, structure, internal layers, magnetic fields, surface features. A planet has geology, chemistry, maybe an atmosphere. But a black hole? 3 numbers completely describe it. In practice, electric charge isn't important for astrophysical black holes. Any significant charge would attract opposite charges from the surrounding environment and neutralize. So really, It's just mass and spin that matter. The most general black hole solution in Einstein's equations is the Kerr-Newman black hole, rotating and charged. But the ones we find in nature are better described as Kerr black holes, rotating but uncharged. The extreme ones, rotating at the maximum possible rate, where the ergosphere nearly touches the event horizon at the equator, are called extremal Kerr black holes. Whether such extremal black holes exist in nature is debated. They'd be extraordinarily difficult to spin up that fast. This simplicity is both beautiful and unsettling. Black holes are the universe's ultimate data shredders. Send in a library containing all human knowledge, and all you get is a tiny increase in mass. Send in a star, a planet, a galaxy worth of complexity, and the black hole gains mass and maybe spins faster. Or do they? This seemingly innocent question, does information truly vanish into black holes, leads us to one of physics' deepest mysteries, one that Stephen Hawking spent decades trying to solve. In 1974, Stephen Hawking dropped a bombshell that changed everything we thought we knew about black holes, that opened up paradoxes we're still trying to resolve 50 years later. He discovered that black holes aren't completely black. This was shocking. The entire definition of a black hole is that nothing can escape from inside the event horizon. Nothing. The math is clear. The geometry is unambiguous. Once inside, there's no way out. And yet, Hawking showed through careful quantum mechanical calculations that black holes emit radiation. It's now called Hawking radiation, and its existence suggests that black holes slowly evaporate over time, eventually vanishing completely. Here's how it works, and it's genuinely one of the most beautiful and strange predictions in all of physics. Quantum mechanics tells us that empty space isn't actually empty. The vacuum, what we think of as nothingness, is actually a seething foam of quantum activity. Virtual particles pop into existence in particle-antiparticle pairs, exist for a tiny fraction of a second, allowed by the Heisenberg uncertainty principle, then annihilate each other and disappear. Normally, this happens so quickly that these virtual particles can't be detected or measured directly. They're quantum fluctuations, borrowing energy from the vacuum temporarily before paying it back. But near a black hole's event horizon, something remarkable can occur. A particle-antiparticle pair appears right at the boundary, right at the edge of the event horizon. One particle falls into the black hole before the pair can annihilate. The other escapes. From an outside observer's perspective, it looks like the black hole is emitting radiation. Particles are escaping from near the horizon. But wait, you might ask, doesn't this violate conservation of energy? Particles are escaping, carrying energy away. Where does that energy come from? The answer is subtle and beautiful. The particle that fell into the black hole has negative energy as measured from infinity. This is possible near the horizon because of the severe space-time curvature. By absorbing negative energy, the black hole loses mass. The escaping particle carries away positive energy, and the total energy of the system is conserved. This radiation carries energy away from the black hole, meaning the black hole must lose mass. Very, very slowly, black holes evaporate. The temperature of this Hawking radiation is inversely proportional to the black hole's mass. Massive black holes are extremely cold, far colder than the cosmic microwave background, the afterglow of the Big Bang that fills all space at about 2.7 Kelvin. For a stellar mass black hole of 10 solar masses, the temperature is about 6 billionths of a Kelvin. It's so cold that it actually absorbs more energy from the cosmic microwave background than it radiates through Hawking radiation. These black holes are currently growing, not shrinking. Only in the far future, after the universe has expanded and cooled enough that the cosmic microwave background temperature drops below the Hawking temperature, will these black holes begin to evaporate. How long does evaporation take? The lifetime of a black hole, through Hawking radiation, is proportional to the cube of its mass. For a stellar mass black hole of 10 solar masses, the evaporation time is approximately 10 to the power of 67 years. That's 10 followed by 67 zeros. For context, The current age of the universe is only about 10 to the power of 10 years, about 14 billion years. So we're talking about timescales incomprehensibly longer than the current age of reality. The universe would have to age by a factor of 10 quadrillion trillion trillion trillion, 10 to the power of 57, before a stellar mass black hole evaporates. For supermassive black holes like Sagittarius A*, the evaporation time is even more absurd, approximately 10 to the power of 100 years or more. These are timescales that mock human comprehension, that make the entire current history of the universe seem like the blink of an eye. But tiny black holes? If micro-black holes exist and are small enough, they'd evaporate in a flash. A black hole with the mass of a mountain might evaporate in a fraction of a second in an explosive burst of radiation. This was the concern, unfounded, as it turned out, when the Large Hadron Collider was being built, that high-energy collisions might create micro-black holes. But even if they could, which requires exotic physics that probably doesn't exist, they'd evaporate so quickly they'd be completely harmless, existing for far less time than it takes light to cross an atomic nucleus. Now, as the black hole evaporates, it shrinks. And as it shrinks, it gets hotter. The temperature increases, so it radiates faster. The evaporation accelerates. The final moments of a black hole's life would be dramatic. A runaway process as the black hole becomes smaller, hotter, and radiates faster and faster. The last second of evaporation would release more energy than the previous million years. The final explosion would be spectacular, releasing all the remaining mass energy in a burst of radiation. All of this is beautiful and consistent, except for one problem. One profound, deeply troubling problem that physicists have been arguing about for 50 years. The information paradox. Quantum mechanics has a fundamental principle. Information is never truly destroyed. The state of a quantum system is always, in principle, recoverable. If you know the exact quantum state of a system at one time, you can in principle calculate its state at any other time, forward or backward. Information is conserved. This isn't just a preference or a guideline. It's baked into the mathematical structure of quantum mechanics through unitary evolution. Quantum mechanics is reversible. Information cannot be lost. But black holes seem to violate this principle. Imagine you throw a book into a black hole. That book contains information, the arrangement of atoms, the text on its pages, the quantum states of every particle composing it. The information crosses the event horizon and vanishes. Now wait 10 to the power of 67 years for the black hole to evaporate through Hawking radiation. The black hole shrinks and finally vanishes in a burst of radiation. Where did the information go? The Hawking radiation is thermal. It has no structure, no information content beyond temperature and particle types. It's random, like the heat coming off a hot stove. The information about the book seems to have been destroyed. This violates quantum mechanics' fundamental principle of information conservation. You might think, well, the information is still inside the black hole. But eventually the black hole evaporates completely. It vanishes. Where is the information then? This is the information paradox, and it's not just an academic curiosity. It's a fundamental conflict between quantum mechanics, which says information must be conserved, and general relativity, which says anything crossing the event horizon is lost. Hawking initially argued that information really is destroyed, that black holes are the one exception to quantum mechanical information conservation. This would require modifying quantum mechanics at a fundamental level. Most physicists found this unsatisfying. Quantum mechanics works too well, is too fundamental, is too deeply tested to just throw out one of its core principles because of black holes. So what's the resolution? Decades of work have led to several proposed solutions, though none are definitively proven. The information is encoded in Hawking radiation itself, in subtle correlations. Early Hawking radiation might be entangled with later Hawking radiation in incredibly complex ways that encode all the information about what fell in. The radiation isn't as random as it appears. There are subtle quantum correlations that preserve information. Recent work on soft hair, and other quantum effects at the horizon suggests mechanisms by which information might be imprinted on outgoing radiation. The information is stored on the event horizon. The holographic principle emerged from these discussions. This principle suggests that all the information contained in a volume of space can be described by information encoded on the boundary of that space, like a three-dimensional image encoded in a two-dimensional hologram. For a black hole, all the information about what fell in might be encoded on the two-dimensional event horizon surface. As the black hole evaporates and the horizon shrinks, this information is gradually transferred to the Hawking radiation. This leads to a profound idea. Our three-dimensional universe might be a hologram, with all information fundamentally encoded on a distant two-dimensional surface. Black holes might be telling us something deep about the nature of reality itself. The information escapes through quantum entanglement. Recent work suggests that the infalling matter and the Hawking radiation might be quantum mechanically entangled in ways that preserve information. The radiation and the black hole interior might not be as separate as classical general relativity suggests. This is related to the ER equals EPR conjecture, the idea that entangled particles might be connected by tiny wormholes, Einstein-Rosen bridges, linking quantum entanglement, EPR, to general relativity geometry, ER. Black holes don't completely evaporate. Some theories suggest a tiny remnant remains after evaporation, a Planck-scale object that contains all the information. This seems contrived, but can't be ruled out. Firewalls and complementarity. Some solutions propose that the event horizon isn't as smooth as classical relativity suggests. There might be a firewall, a region of intense energy at the horizon that destroys information in a different way, though this has its own problems. The truth is, we don't know the answer yet. The information paradox remains one of the deepest problems in theoretical physics. Its resolution will likely require a complete theory of quantum gravity, a framework that unifies quantum mechanics and general relativity. Several approaches are being pursued. String theory suggests that fundamental particles aren't point-like, but are tiny vibrating strings. It naturally includes gravity and quantum mechanics, and might resolve the information paradox by showing how information is preserved in the full string-theoretic description of black holes. Loop quantum gravity takes a different approach, quantizing spacetime itself, suggesting that space and time are discrete at the smallest scales. In this framework, the singularity might be smoothed out by quantum effects, and information might be preserved differently. Other approaches include causal set theory, asymptotically safe gravity, and various others, each trying to marry quantum mechanics and gravity. What's clear is that black holes are telling us something profound. They're the testing ground where quantum mechanics and general relativity clash most directly. They're pointing toward new physics, toward a deeper understanding of reality. The holographic principle that emerged from black hole physics has become central to modern theoretical physics. It suggests that our intuitions about space and dimensionality might be wrong, that information and reality might work in fundamentally different ways than we thought. Black holes sit at the intersection of the two great pillars of 20th century physics. Quantum mechanics governs the realm of the very small, atoms, particles, fields. General relativity governs the realm of the very large and very massive, planets, stars, galaxies, the universe itself. These two theories are both spectacularly successful within their domains. Quantum mechanics has been tested to absurd precision, predictions matching experiments to 10 decimal places or more. General relativity has been confirmed through countless tests, from GPS satellites to gravitational waves to black hole images. But they're fundamentally incompatible. They can't both be right in their current forms, because they give different answers in extreme situations like black holes or the Big Bang. Solving the information paradox and understanding black holes at the quantum level might be the key to the next revolution in physics, a theory of everything that unites quantum mechanics and gravity, that describes the universe at all scales, from the smallest quantum fluctuations to the largest cosmic structures. For now, black holes remain the universe's greatest laboratories for extreme physics. They contain singularities where our equations fail. They emit radiation that challenges our understanding of information and quantum mechanics. They bend spacetime to its breaking point and twist reality into impossible geometries. And we're about to experience all of that firsthand. But first, let's see what they do to the space around them. Before we descend into our chosen black hole, before we cross that final boundary, let's take time to appreciate what happens around a black hole when it feeds. Because that's where the real spectacle is, where some of the most violent and energetic phenomena in the entire universe unfold. When a black hole is actively feeding, pulling in gas, dust, whole stars torn apart by tidal forces, it creates one of the most violent and luminous phenomena in the cosmos, the accretion disk. As matter spirals toward the black hole, it doesn't fall straight in. Conservation of angular momentum, the same principle that makes a spinning ice skater spin faster when they pull their arms in, forces the material into a disk, rotating faster and faster as it approaches the event horizon. Think of it like water spiraling down a drain, except the water is gas heated to millions of degrees and the drain is a hole in spacetime itself. Particles in this disk rub against each other, creating friction. And friction creates heat. Tremendous heat. Viscosity and magnetic fields transfer angular momentum outward, allowing matter to spiral inward while heating up in the process. The inner regions of an accretion disk around a stellar mass black hole can reach temperatures of millions of degrees Celsius, hot enough to strip atoms of their electrons, creating a plasma of bare nuclei and free electrons. At these temperatures, matter doesn't emit visible light. It emits X-rays and gamma rays, the highest energy forms of electromagnetic radiation. For supermassive black holes, the temperatures can be even more extreme in absolute terms, though the spectrum depends on the feeding rate and disk structure. This is the irony of black holes, the cosmic joke. They're the darkest objects in existence, the ultimate in blackness, yet their feeding process creates some of the brightest objects known. The most luminous objects in the universe are feeding black holes. A supermassive black hole consuming matter at a high rate, what we call a quasar, can outshine its entire host galaxy by factors of 100 or even 1000. We're talking about billions of stars dimmed by comparison to the blazing inferno of gas, dying at the event horizon of a single supermassive black hole. The brightest quasars are visible across the observable universe. We can detect them from billions of light-years away, seeing them as they were when the universe was young, when galaxies were still forming and black holes were growing rapidly. But the accretion disk, as spectacular as it is, isn't the only phenomenon around feeding black holes. Some black holes create something even more remarkable. Some black holes launch jets, narrow beams of particles and radiation accelerated to nearly the speed of light, shooting out perpendicular to the accretion disk like cosmic blowtorches. These jets can extend for thousands, even millions of light-years, punching through intergalactic space, creating enormous bubble-like structures in the surrounding gas. The jet from the galaxy M87, the same galaxy whose black hole we photographed in 2019, extends for at least 5,000 light-years, visible in optical and radio wavelengths. Other jets extend even farther, creating radio lobes that dwarf their host galaxies. How do jets form? We don't fully understand the mechanism, but the leading theory involves magnetic fields. As matter spirals in the accretion disk, it drags magnetic field lines with it, twisting them into helical shapes. These twisted magnetic fields act like particle accelerators and collimators, funneling matter and energy along the rotation axis of the black hole. The black hole's rotation might power the jet through the Blandford-Znajek process, a mechanism that extracts rotational energy from the spinning black hole using magnetic fields threading the event horizon. It's a version of the Penrose process, but using electromagnetic fields instead of particles. The result is a narrow beam of plasma moving at 99% of the speed of light or faster, appearing to move faster than light due to relativistic effects when aimed nearly toward us. These jets carry enormous power, sometimes equivalent to trillions of suns, channeling the gravitational energy of infalling matter into coherent beams that can affect galaxy-scale regions. When a jet happens to point toward Earth, when we're looking down the barrel of the cosmic gun, we see a blazer. Blazers are among the brightest, most variable objects in the sky. The jet's emission is beamed toward us, amplified by relativistic effects, creating extreme brightness that can change on timescales of hours or days. The fastest variations we see in blazers suggest that the emission regions are incredibly compact, light hours or light days across, implying enormous energy density and magnetic field strength. Then there are tidal disruption events, perhaps the most dramatic meals a black hole can have, and some of the most spectacular transient events in astronomy. When a star wanders too close to a supermassive black hole, tidal forces become strong enough to overcome the star's gravity. The side of the star facing the black hole feels significantly stronger gravity than the far side. This difference, the tidal force, can literally pull the star apart. The star is spaghettified, just like an unfortunate astronaut would be, but on a stellar scale. The star stretches, elongates, and is shredded into a stream of gas. About half of the star's material is flung away into space at high velocity, escaping the black hole entirely. The other half is captured, pulled into an accretion disk around the black hole. As this stellar debris settles into an accretion disk and begins to be consumed, it creates a bright flare observable across the universe. We see a sudden brightening in X-rays, ultraviolet, and optical light that peaks over weeks and fades over months as the stellar debris is gradually consumed. These events are rare, maybe one per galaxy, every 10,000 to 100,000 years on average. But in a universe with trillions of galaxies, we can detect several per year by surveying large areas of sky. Each tidal disruption event is like a cosmic autopsy, allowing us to study both the black hole, its mass and spin affect how the disruption occurs, and the star. Different types of stars produce different flare characteristics. We've even detected evidence of tidal disruption events that launched jets. The stellar debris somehow triggering jet formation in previously quiet black holes, adding yet another layer of complexity to these phenomena. Black holes also affect their surroundings in more subtle, but equally important ways. They can gravitationally lens light from objects behind them, bending and magnifying light like a cosmic magnifying glass. Einstein predicted this in 1915, and gravitational lensing by black holes has now been observed numerous times. When a black hole passes in front of a more distant star, from our perspective, the black hole's gravity bends light from the star around it, creating a characteristic brightening pattern called microlensing. This allows us to detect isolated black holes that have no accretion disk and emit no light. The Gaia satellite and other surveys are finding these isolated black holes through their gravitational lensing signatures, slowly building a census of the hidden black hole population. The shadow of a black hole, what we saw in the Event Horizon Telescope images of M87* and Sagittarius A*, appears larger than the event horizon itself because light is bent around the black hole. Photons passing near the black hole follow curved paths through spacetime. Some photons that pass just outside the photon sphere manage to escape, but are bent significantly, creating a dark region. The shadow, about 2.6 times the Schwarzschild radius in diameter for a non-rotating black hole. For a rotating black hole, the shadow is asymmetric, slightly larger on one side, and this asymmetry tells us about the black hole's spin. The bright ring around the shadow, what we see in the EHT images, comes from photons on orbits that almost fell in, but managed to escape, looping partially around the black hole before escaping to reach us. This is why the ring appears on the opposite side from where the accretion disk is brightest in physical space. We're seeing light bent around from behind. Black holes in binary systems create their own intricate dynamics. In X-ray binaries, a black hole pulls material from a companion star in a steady stream, creating a bright X-ray source that we can study in detail. The companion star is slowly being devoured, and the black hole grows, meal by meal, orbit by orbit. Some X-ray binaries show quasi-periodic oscillations, regular fluctuations in brightness at specific frequencies, that might be caused by matter oscillating or precessing in the inner accretion disk. These oscillations give us information about the strong field gravity very close to the event horizon. Sometimes, black holes violently eject their companion stars through gravitational interactions. A star passing near a binary black hole system can gain enough velocity through a gravitational slingshot to escape the galaxy altogether, becoming a hypervelocity star racing through intergalactic space at thousands of kilometers per second. We've found dozens of these hypervelocity stars, some moving fast enough to escape the Milky Way's gravity entirely. They're likely refugees from close encounters with Sagittarius A** or other massive black holes, flung out like stones from a slingshot. But perhaps the most violent interactions occur when black holes meet each other, when two of these cosmic titans spiral together in a dance of mutual destruction. When two black holes orbit each other, they lose energy by emitting gravitational waves, ripples in spacetime itself predicted by Einstein in 1916. These waves carry energy away from the system, causing the black holes to spiral closer together over time, orbiting faster and faster in an inexorable death spiral. For stellar mass black holes orbiting each other, the in-spiral can take billions of years if they start far apart. But as they get closer, the process accelerates. In the final hour before merger, they're orbiting each other hundreds of times, releasing gravitational wave power equivalent to thousands of suns. In the final second, they're whipping around each other hundreds of times per second, releasing more energy in gravitational waves than all the stars in the observable universe emit in light. Then they collide. Their event horizons merge into one. The space-time around them ripples and oscillates, ringing like a struck bell in what's called the ring-down phase. And then silence. A single, larger black hole remains, slightly less massive than the sum of its parents, because several solar masses of energy have been radiated away as gravitational waves during the final moments. This is what LIGO and Virgo detect. The gravitational wave signature of these cosmic collisions, the ripples in spacetime washing over Earth billions of years after the events that created them. On September 14, 2015, at 9 hours 50 minutes and 45 seconds Coordinated Universal Time, two detectors in the United States, one in Livingston, Louisiana, one in Hanford, Washington, simultaneously registered an unusual signal. It lasted less than a second. A distinctive chirp rising in frequency and amplitude, exactly matching the theoretical prediction for two black holes spiraling together and merging. The signal traveled through both detectors, arriving at Livingston 7 milliseconds before reaching Hanford, consistent with a gravitational wave propagating at the speed of light from a source in the southern sky. In that fraction of a second, in that brief chirp, humanity entered a new era. We had detected gravitational waves. This wasn't just another astronomical discovery. This was the opening of an entirely new window on the universe. For all of human history, for every prior civilization that had looked up at the sky, we had explored the cosmos through electromagnetic radiation, light in all its forms. But gravitational waves are different. They're ripples in spacetime itself, oscillations in the fabric of reality propagating at the speed of light. They don't scatter or get absorbed like light. They pass through matter almost completely unimpeded, carrying information from regions of spacetime inaccessible to any telescope. The signal, designated GW150914, for the date it was detected, came from two black holes that had been orbiting each other 1.3 billion light-years away, back when Earth was still dominated by simple multicellular organisms, long before the first fish, before the first plants colonized land. For millions or billions of years, these black holes had been spiraling together, slowly losing energy to gravitational waves, their orbits decaying, bringing them closer and closer together. In their final moments, as they approached merger, They were releasing gravitational wave power equivalent to 10 to the power of 50 watts, more power than all the stars in the observable universe combined emit in light. For a brief fraction of a second, this binary system was the most powerful energy source in the universe. The two black holes had masses of 36 and 29 solar masses. When they merged, the resulting black hole was 62 solar masses, 3 solar masses lighter than the sum of its parents. Where did those 3 solar masses go? Into gravitational wave energy. E equals mc squared. 3 suns' worth of mass energy converted directly into ripples in spacetime, radiating outward at the speed of light. Those ripples traveled across the cosmos for 1.3 billion years. They passed through gas clouds and galaxies. They traversed the expanding universe, their frequency stretching with cosmic expansion. And on September 14, 2015, they reached Earth. When they passed through Earth, they compressed and stretched space by less than 1,000th the diameter of a proton. The entire planet oscillated, squeezed and stretched in an alternating pattern, and LIGO detected it. LIGO, the Laser Interferometer Gravitational Wave Observatory, is one of the most remarkable scientific instruments ever built, a triumph of engineering that pushes technology to its absolute limits. Each LIGO detector is an L-shaped structure with arms 4 kilometers long. Laser beams travel down each arm, bounce off mirrors, and return to the vertex where they interfere. Normally, they're tuned so the light from the 2 arms destructively interferes, creating darkness at the detector. But when a gravitational wave passes through, it compresses space in one direction while stretching it in the perpendicular direction. This changes the arm lengths by tiny amounts, far smaller than an atomic nucleus, which shifts the interference pattern, creating a measurable signal. The precision is absurd. LIGO can measure changes in distance smaller than 10 to the power of -19 meters, about 1/10,000th the diameter of a proton. Imagine measuring the distance to the nearest star to within the width of a human hair. That's the kind of precision we're talking about. Achieving this requires isolating the mirrors from every possible source of vibration, seismic noise, thermal fluctuations, quantum noise, even the gravitational pull of passing clouds. The mirrors are suspended in elaborate multi-stage pendulums. The entire system is in ultra-high vacuum. Active seismic isolation systems compensate for ground motion. And it worked. Against enormous odds, despite decades of effort and hundreds of millions of dollars invested, it worked. The 3 scientists who led the project, Rainer Weiss, Barry Barish, and Kip Thorne, received the 2017 Nobel Prize in Physics, awarded barely 2 years after the first detection. The Nobel Committee recognized not just the detection itself, but the opening of an entirely new field of astronomy. A century after Einstein predicted gravitational waves, 99 years after he expressed doubt they could ever be detected, we had finally confirmed their existence. But GW 150914 was just the beginning, just the first of many discoveries. Since September 2015, LIGO and its European counterpart Virgo, a similar detector in Italy, have detected dozens upon dozens of black hole mergers, each one providing unique insights into these extreme objects. We've found black holes larger than we thought stellar collapse could produce, some up to 100 solar masses or more. Theoretical models of stellar evolution didn't predict stars could form black holes that massive. Something about our understanding is incomplete. We've detected mergers at different distances, allowing us to map the distribution of black holes through cosmic history. We've found mergers with unusual mass ratios, one black hole much larger than the other, testing how black holes pair up and merge. We've detected precession, the spin axes of the black holes changing direction as they spiral together, giving us information about how these systems formed. And in 2017, we detected something even more remarkable. GW 170817, the merger of 2 neutron stars. Unlike black hole mergers, which emit only gravitational waves, because black holes have no magnetic fields, no surface, nothing to emit light. Neutron star mergers also produce electromagnetic radiation. The collision creates heavy elements through rapid neutron capture, our process nucleosynthesis, producing gold, platinum, uranium, many of the heaviest elements in the periodic table. The gravitational wave signal was detected by LIGO and Virgo. Within seconds, gamma-ray satellites detected a burst of gamma rays from the same direction. Within hours, optical telescopes saw the afterglow, a kilonova, from the radioactive decay of newly synthesized heavy elements. This was the first multi-messenger astronomy event involving gravitational waves. The same event observed through multiple channels, both gravitational and electromagnetic. The observations confirmed that neutron star mergers are indeed the source of most heavy elements in the universe. Every gold ring, every platinum catalyst, every uranium atom on Earth was forged in events like this. Neutron stars colliding and creating heavy elements in the incredible conditions of their merger. The sound of gravitational waves, created by converting the signal into audio frequencies, is haunting and beautiful. A black hole merger creates what's called a chirp, a rising pitch that accelerates, climbs higher and higher, then suddenly cuts off as the black holes merge. It sounds like a bird chirping or a drop of water falling into a pool. That sound is the sound of space-time itself screaming, the acoustic signature of two objects with the mass of dozens of suns colliding at nearly the speed of light. Each gravitational wave detection is a story. GW150914, the first, told us that 30-plus solar mass black holes exist and can find each other and merge. GW170817 told us that neutron star mergers create heavy elements and that gravitational waves travel at the speed of light, to within 1 part in 10 to the power of 15. GW190521 detected the merger of black holes so massive, 85 and 66 solar masses, that one or both might have been formed from previous mergers, hints of hierarchical black hole formation. We've discovered an entire hidden population of black holes that we never knew existed. Before LIGO, we knew about a few dozen stellar mass black holes from X-ray binaries. Now we've detected mergers of black holes we would never have found through electromagnetic astronomy. Isolated binary black holes in the darkness between stars, invisible except through their gravitational wave emission. Gravitational wave astronomy doesn't just tell us that black holes exist and merge. It tells us their masses to within a few percent. It tells us their spins, how fast they're rotating. It tells us their distances through the amplitude of the signal. It lets us study the merger process in exquisite detail, how the orbit decays, how the black holes spiral, how they merge, how space-time rings down afterward. We're learning things we could never learn from electromagnetic observations alone. And we're just getting started. The current detectors are being upgraded. Advanced LIGO Plus and Advanced Virgo Plus will be more sensitive, detecting mergers from farther away, seeing more events, building better statistics. New detectors are being built. Kagra in Japan is already operating, contributing to the global network. LIGO India is under construction, adding another detector to improve sky localization. Next-generation ground-based detectors are being planned. The Einstein telescope in Europe will be built underground in a triangular configuration, with arms 10 kilometers long, sensitive to frequencies lower than current LIGO. Cosmic Explorer in the US will have arms 40 kilometers long, 10 times longer than current LIGO, detecting mergers from across the observable universe. These next-generation detectors won't just find more events. They'll detect supermassive black hole mergers. No, wait, that's not quite right. Ground-based detectors are sensitive to high frequencies, tens to thousands of hertz, perfect for stellar mass black holes. Supermassive black hole mergers produce gravitational waves at much lower frequencies, millihertz to microhertz, that ground-based detectors can't access because of seismic noise. For supermassive black hole mergers, we need a space-based detector. Enter LISA, the Laser Interferometer Space Antenna. LISA is a planned ESA/NASA space mission scheduled to launch in the 2030s. It will consist of 3 spacecraft flying in a triangular formation, separated by 2.5 million kilometers, about 6 times the Earth-Moon distance, forming a giant interferometer in space. With arms millions of kilometers long, LISA will be sensitive to low-frequency gravitational waves from supermassive black hole mergers across the entire observable universe. We'll detect the mergers of black holes with millions or billions of solar masses, events that occur when galaxies collide and their central black holes spiral together. We'll see these mergers from the edge of the observable universe, mapping how supermassive black holes formed and evolved over cosmic history. We'll also detect extreme mass ratio in spirals, stellar mass objects spiraling into supermassive black holes, which will map the spacetime around supermassive black holes with extraordinary precision, testing general relativity in the strongest possible gravitational fields. LISA will detect binary white dwarfs throughout our galaxy, thousands of them, creating a confusion noise background, but also giving us a census of these systems. And LISA might even detect gravitational waves from the Big Bang itself, primordial gravitational waves from cosmic inflation, if the amplitude is high enough. These would carry information about the universe's first moments, about physics at energy scales we could never reach in particle accelerators. We've gone from detecting nothing to detecting dozens of mergers in less than a decade. In another decade, we'll be detecting thousands per year. We'll build statistical maps of black hole populations, study how they form and evolve, test general relativity with unprecedented precision. Gravitational wave astronomy is like suddenly gaining a new sense. For all of human history, we've explored the universe through light, optical, infrared, radio, X-ray, gamma-ray, all different wavelengths of electromagnetic radiation. Now we can listen to it. We can hear the universe's most violent events, the collisions and catastrophes that light alone could never reveal. We can detect objects that emit no light at all, black holes in the darkness, invisible except through the ripples they create in spacetime. And what we're hearing is extraordinary. The universe is more violent, more dynamic, more populated with extreme objects than we ever imagined. The chirps of merging black holes are like a cosmic symphony, each one unique, each one telling a different story about where it came from, how it formed, what it's made of. And we're only just beginning to learn the language. Black holes aren't just cosmic curiosities or astronomical objects to catalogue and study. They're the universe's most extreme physics laboratories, natural experiments that test our theories under conditions we could never create artificially. Every prediction of general relativity is tested in its most extreme form near a black hole. Time dilation taken to its limit. Gravitational redshift amplified to infinity. Frame dragging becomes dominant. Gravitational waves are maximized, all pushed to their absolute theoretical limits. And so far, Einstein keeps winning. Scientists studying the stars orbiting Sagittarius A** have used their observations to test Einstein's theory in the strongest gravitational field accessible to detailed observation. One star in particular, called S2 or S0-2 in Andrea Gheza's catalogue, has become the Rosetta Stone for these tests. S2 has an elliptical orbit with a period of about 16.05 years. At its closest approach, called pericenter, it comes within just 17 light-hours of Sagittarius A**, about 4 times the distance from the Sun to Neptune, moving at about 3% of the speed of light, roughly 8,000 kilometers per second. This is an extraordinary opportunity. S2's closest approach brings it deep into the gravitational well of a 4-million solar mass black hole, where relativistic effects should be strong and measurable. During S2's closest approach in May 2018, scientists measured the gravitational redshift of light from the star, the stretching of wavelengths as photons climb out of the deep gravitational well. General relativity predicts that light should be redshifted by a specific amount depending on how deep in the gravitational well it originates. The redshift should follow the formula Z equals 1/square root 1-2 gm/rc superscript 2, 1, where m is the black hole's mass R is the distance from the black hole, G is the gravitational constant, and C is the speed of light. The measurements matched Einstein's predictions perfectly, to within the measurement uncertainties of about 10%. The observed redshift was exactly what general relativity predicted. Newtonian gravity would predict no redshift at all. Special relativity alone would give the wrong answer. Only general relativity gets it right. They also detected relativistic precession, the way S2's orbit rotates over time, an effect called the Schwarzschild precession. In Newtonian gravity, a planet in an elliptical orbit traces out the same ellipse every orbit. The orbit closes on itself perfectly. But in general relativity, strong gravity causes the orbit to precess. The ellipse itself rotates slowly over time. This is the same effect that explained the anomalous precession of Mercury's orbit, the observation that made Einstein famous in 1919. Mercury's orbit precesses by 43 arcseconds per century beyond what Newtonian gravity predicts, and general relativity explains this perfectly. For S2, the precession is much larger, several arcminutes per orbit, because the gravitational field is so much stronger. And again, the observations match Einstein's predictions. These aren't subtle effects. These are 10 to 30% corrections to Newtonian gravity, large relativistic effects that are clearly measurable, and that confirm general relativity is correct even in strong gravitational fields. Future observations will test even more exotic predictions. Scientists are hoping to detect frame dragging around Sagittarius A*, the way the rotating black hole drags spacetime around with it, affecting the orbits of nearby stars. They're also looking for deviations from general relativity that might hint at new physics, modifications to gravity at strong fields, quantum corrections, effects from extra dimensions. So far, Einstein keeps winning, but the tests continue. Gravitational wave detections provide even more stringent tests. Each black hole merger observed by LIGO tests general relativity in the most extreme conditions possible: strong gravity, high velocities, large accelerations, regions where spacetime is dynamically oscillating. Scientists analyze the gravitational waveforms and compare them to detailed numerical simulations based on general relativity. They test whether the ring-down phase, the oscillations after merger, matches predictions for how a black hole's event horizon vibrates. They test whether gravitational waves travel at the speed of light. They do, to within 1 part in 10 to the power of 15, confirmed by the joint observation of GW 170817 with electromagnetic counterparts. They test whether black holes really do merge smoothly as predicted, whether their event horizons behave as theory suggests, and whether Einstein's equations correctly describe these extreme events. So far, every test confirms general relativity. The theory passes with flying colors. Whatever replaces or extends general relativity, the quantum gravity theory we don't yet have, must reduce to Einstein's equations in all the regimes we've tested so far. But black holes also challenge our understanding. They sit at the boundary where general relativity and quantum mechanics meet and clash. General relativity works beautifully at large scales and strong gravity, describing planets, stars, galaxies, black holes, and the expansion of the universe. It's been tested exhaustively and passes every test. Quantum mechanics governs the realm of the very small, atoms, particles, fields, quantum fluctuations. It's also been tested exhaustively, to even higher precision than general relativity, and it too passes every test. But at a black hole's singularity, at the Big Bang, in the first moments of cosmic inflation, both realms collide. We need a theory that combines them, and we don't have one yet. This is why physicists are searching for a theory of quantum gravity, a framework that unifies relativity and quantum mechanics, that describes physics at all scales, from quantum fluctuations to cosmic horizons. Several approaches are being pursued, each with different philosophy and methodology. String theory proposes that fundamental particles aren't point-like, but are tiny one-dimensional strings vibrating in 10 or 11 dimensions, with extra dimensions compactified or hidden. Different vibration modes correspond to different particles. String theory naturally includes gravity. One vibration mode is the graviton, the quantum particle of gravity, and it might resolve the singularity by replacing it with extended string scale structures. Loop quantum gravity takes a different approach, quantizing spacetime itself. It suggests that space and time are not continuous but discrete at the Planck scale, about 10 to the power of negative 35 meters, made of tiny loops or atoms of space. In this framework, the singularity might be smoothed out by quantum effects. There might be a quantum bounce at the center of a black hole rather than a true singularity. Other approaches include causal set theory, spacetime as a discrete set of events, asymptotically safe gravity, gravity remains well behaved at all scales, emergent gravity, gravity emerges from more fundamental quantum degrees of freedom, and various others. Each approach makes different predictions about what happens at the Planck scale, about the nature of singularities, about the fate of information in black holes. Future observations, maybe of primordial gravitational waves, maybe of quantum aspects of black hole evaporation, if we could ever detect Hawking radiation directly, maybe of phenomena we haven't predicted yet, might tell us which approach is right. What's clear is that black holes are telling us where our current physics fails, where we need new ideas. The singularity is a place where our equations break down and return nonsensical answers. That's physics' way of saying, I need new physics here. The information paradox, Hawking radiation, the nature of the event horizon. These aren't just puzzles to solve. They're clues pointing toward deeper truths about reality, about the fundamental nature of space, time, matter, and information. Some researchers have even proposed truly wild ideas that might or might not be correct, but that show how strange black holes really are. Could black holes be portals to other universes? Probably not in any practical sense, but the mathematics of rotating black holes, Kerr black holes, does suggest possible interior structures that could theoretically connect to other regions of spacetime. The Kerr solution has what's called a ring singularity, rather than a point singularity, and the math suggests you could theoretically pass through the ring into a region with strange properties. Negative space, maybe even pathways to other universes. This is almost certainly not physical. The interior of a real black hole is probably nothing like the idealized Kerr solution because of instabilities, quantum effects, and the fact that black holes form from collapse rather than being eternal mathematical objects. But it's a testament to how bizarre these objects are that such ideas can even be discussed seriously in the physics literature. The idea that entangled particles might be connected by tiny wormholes, the ER equals EPR conjecture, is another example. Could quantum entanglement, the mysterious connection between particles that allows them to be correlated across vast distances, actually be explained by tiny wormholes connecting them through spacetime? This is speculative, but taken seriously by some of the world's leading theoretical physicists. It would connect quantum mechanics, EPR stands for Einstein-Podolsky-Rosen, a famous paper on quantum entanglement, to general relativity geometry, ER stands for Einstein-Rosen, a paper on wormholes. Black holes have also revealed deep principles about the universe through the holographic principle. The idea that emerged from black hole thermodynamics, suggesting that all information in a volume of space can be encoded on the boundary of that region. This principle, if true, would be profound. It would mean that our three-dimensional world is in some sense a hologram, a projection from information encoded on a two-dimensional surface. This isn't just philosophy. It's led to concrete research programs like the ADS/CFT correspondence in string theory, which relates gravitational theories in higher dimensional spaces to quantum field theories on lower dimensional boundaries. Black holes might be telling us something fundamental about how information, space, and quantum mechanics are related at the deepest level. They might be revealing that space itself is emergent, not fundamental, that spacetime arises from more basic quantum information theoretic principles. These ideas are still speculative, still being developed, still debated. But they all originate from taking black holes seriously, from following the implications of what we've learned about these objects. Black holes are laboratories for testing physics in the most extreme conditions possible in nature. They're challenging our theories, pushing them to their limits, revealing where new physics is needed. And they're doing something else too, showing us that we, fragile carbon-based life forms on a tiny planet orbiting a medium-sized star in an average galaxy, can nevertheless understand the most extreme objects in the universe through mathematics and observation. We can map their properties, test predictions, photograph their shadows, and hear their collisions across billions of light years. That's worth celebrating. That's extraordinary. But understanding them intellectually is one thing. Experiencing them directly, that's what we're here for. It's time to descend. We've chosen our target carefully. A supermassive black hole similar to Sagittarius A*, with a mass of approximately 4 million suns, roughly 12 million kilometers in Schwarzschild radius. Why supermassive? Why not experience the descent into one of the smaller, more common stellar mass black holes? The answer is survival, or at least experiencing the journey long enough to appreciate it. A stellar mass black hole would rip us apart through spaghettification long before we reach the event horizon. The tidal gradient, the difference in gravitational pull between our head and feet, would become strong enough to tear our bodies apart atom by atom while we're still outside the black hole, still in normal space where escape is theoretically possible. We'd die kilometers away from the event horizon, never experiencing what lies beyond. But with a supermassive black hole, the tidal gradient at the horizon is gentle enough that we can cross intact, alive, conscious. We'll have time, precious minutes, to experience what no electromagnetic signal can ever report back, to see what happens beyond the point of no return. We'll survive long enough to witness the impossible. We begin our approach from a safe distance, several million kilometers away, about 10 times the Schwarzschild radius, where gravity is strong but not yet overwhelming. From here, the black hole is invisible. No light escapes from within the event horizon, so we see it only as a perfect circle of darkness against the stars, a hole in the heavens, utterly black, darker than anything we've ever seen, because it's not merely the absence of light, but the absence of space itself. Around this darkness is a faint, glowing ring, the accretion disk. For our particular black hole, the disk is relatively dim. This black hole isn't feeding actively. It's not a quasar, just a thin trickle of gas spiraling inward, heated to a few million degrees, emitting primarily in X-rays and ultraviolet. The ring appears to surround the darkness completely because of gravitational lensing. Light from the back of the disk is bent around the black hole, allowing us to see both the front and back simultaneously, creating the characteristic ring structure. We begin to fall. Initially, the acceleration is gentle. At this distance, the gravity is strong, but not dramatically different from the gravitational acceleration we might experience near a massive star. We fall inward, picking up speed steadily. As we fall closer, gravity strengthens. We're accelerating faster now, tens of kilometers per second, then hundreds. There's no air resistance in space to slow us down, nothing to impede our fall. We're in free fall, weightless from our perspective, but accelerating relative to distant stars. Time begins to slow down relative to the outside universe. Not enough to notice yet, but measurably. If we had a radio connection to observers far away, monitoring our signal, they would detect our clock ticking slightly slower than theirs. Our radio transmissions would be gravitationally redshifted, stretched to longer wavelengths. The effect is subtle at first. At 5 times the Schwarzschild radius, our clock runs at about 95% the rate of clocks far from the black hole. We've lost 5% of our time rate. We don't feel any different. From our perspective, time passes normally, but we're falling deeper into the gravitational well where time itself runs slower. The accretion disk becomes brighter, more detailed as we approach. We can see structure now, swirls and eddies of glowing plasma, heated to millions of degrees by friction and magnetic field compression. The disk is thin, nearly edge-on from our approach angle, creating a luminous ring that seems to grow larger as we fall closer. We're falling faster now, thousands of kilometers per second. At these velocities, relativistic effects start to become noticeable. Stars ahead of us appear slightly blue-shifted, compressed to shorter wavelengths, while stars behind us appear red-shifted. We're moving fast enough that Doppler effects are significant. As we approach closer, 3 times the Schwarzschild radius, something strange happens to our view. The black hole's shadow grows larger, distorted and magnified by gravitational lensing. Light from the accretion disk is bent dramatically around the black hole. We see light from behind the black hole curved around both sides, creating multiple images, a luminous halo that seems to surround the darkness from all directions. The gravitational lensing creates a bizarre, distorted view of the universe. Light rays are bent into complex paths. We see parts of the accretion disk that should be hidden from view, wrapped around by curved spacetime. The stars behind us, the universe we came from, appear compressed into a shrinking circle. All the stars, all the galaxies in that direction, bunched together by gravitational lensing into an ever smaller region of sky. Ahead of us, stars appear to spread apart, distorted by the opposite lensing effect. We're seeing the universe through the warped geometry of spacetime itself, through a cosmic funhouse mirror created by 4 million suns worth of mass compressed into a region smaller than a typical orbit of Mercury. At twice the Schwarzschild radius, time dilation is becoming very significant. Our clock is now running at only about 70% the rate of distant clocks. For every hour that passes for us, an hour and a half passes in the outside universe. The photon sphere passes us, 1.5 Schwarzschild radii from the singularity. This is where light itself can orbit the black hole, where photons move in circular paths around the gravitational well. If we had entered at precisely the right trajectory, with precisely the right velocity, we could have orbited here temporarily, circling the black hole as light does. But we're not orbiting. We're falling, our trajectory taking us inexorably inward. At the photon sphere, we would theoretically be able to see our own back. Photons from behind us curve around the black hole and return to our eyes. The view would be impossible, disorienting, a closed loop of vision showing ourselves from behind. But we're moving too fast, falling too directly to appreciate this fully. We pass through the photon sphere in seconds. Time dilation is extreme now. At 1.2 times the Schwarzschild radius, our clock runs at less than half the speed of distant clocks. 2 hours pass outside for every hour we experience. The accretion disk is intensely bright now, blazing with X-rays and gamma rays that would kill us instantly if this were real, if we weren't protected by our thought experiment, our imagined shields. We can see individual orbits of matter in the inner disk, hot plasma whipping around at significant fractions of the speed of light, completing circuits in minutes, heated to tens of millions of degrees by friction and compression. The innermost stable circular orbit passes us, the last place where matter can orbit stably. Beyond this point, at about 1.001 times the Schwarzschild radius, for our nearly non-rotating black hole, no stable orbit exists. Matter either escapes or falls. There's no middle ground, no equilibrium. We're committed now in a practical sense, even though we're still outside the event horizon. Our velocity is so high, our trajectory so steep, that even if we had rocket engines powerful enough, we couldn't escape. We'd need to accelerate to more than the local speed of light to break free. The universe behind us has compressed into a tiny circle of light directly overhead. All the stars, all the galaxies in that direction, squeezed by gravitational lensing into a region smaller than our fist held at arm's length. That circle shows us the entire outside cosmos, blue-shifted and time-accelerated. We're watching the universe age, seeing it in fast-forward, days passing in what seem like seconds to us. And ahead, growing larger with every moment, is the event horizon. It's not a physical surface. There's no membrane, no barrier, no gate, no wall. It's simply a mathematical boundary in spacetime, the point where the escape velocity equals the speed of light, where outward-pointing light cones tip over and point inward. From outside, observers watching us see something entirely different. They see us slow down. Our movements become sluggish, like a video playing in slow motion. Our rocket engines, if we were firing them, produce diminished thrust as their exhaust redshifts and loses energy. Our clock, visible to them via our transmitted signals, ticks slower and slower compared to theirs. Hours for us seem like days to them, then weeks, then months. Eventually, from their perspective, we appear to freeze at the horizon. Our image becomes permanently imprinted on the event horizon, like a photograph slowly fading. Our light becomes increasingly redshifted, stretched from visible to infrared to radio waves to wavelengths meters long, then kilometers, then astronomical units. We dim. We fade. We redshift into invisibility. From their perspective, we approach the horizon asymptotically, getting arbitrarily close but never quite reaching it, taking literally infinite time to cross as measured by their clocks. They never see us cross. They never receive any signal from us after crossing. From their perspective, we're frozen at the horizon forever, our information spread across the event horizon surface, gradually fading from view. But from our perspective, something completely different happens. We cross the event horizon smoothly, without any indication that we've passed the point of no return. There's no discontinuity, no sensation of passing through anything. Our clock ticks normally from our perspective. It always has, it always will. We don't feel time dilated because we're in our own reference frame. The event horizon passes us like a ghost, invisible, intangible, marking a boundary in space-time that has no local physical signature. If we looked at our instruments, they'd show nothing unusual. Locally, space-time seems perfectly normal. The curvature is there, we could measure it with sensitive instruments. But there's no barrier, no wall, no indication that we've crossed into a region from which escape is impossible. And yet, something fundamental has changed. We are now inside the event horizon. We are beyond the point of no return. If we look back at the universe we came from, we'd see it compressed into a shrinking circle above us, still visible, still sending us light. We could watch it for our remaining minutes, watch the universe age billions of years in our final moments. The circle shows the entire observable universe in that direction, all of cosmic history playing out in accelerated time. Stars are born and die. Galaxies merge. The universe expands. We're seeing the future of the cosmos, compressed and accelerated by our extreme time dilation and the gravitational lensing of light rays that can still reach us. But the fundamental change, the thing that makes this region so different, is this. The singularity is no longer a location in space. It's a moment in our future. Outside the horizon, the singularity was a place, a point in space we could, in principle, avoid by choosing our trajectory carefully, by firing rocket engines, by moving sideways. Inside the horizon, the singularity is a time, a moment we will reach no matter what we do, no matter which direction we point our rockets, no matter how we struggle. Just as you cannot avoid tomorrow, we cannot avoid the singularity. All paths through space-time inside the event horizon lead to the singularity. The geometry itself has changed. What we think of as spatial directions, outside the horizon, up, down, left, right, have different meanings here. The radial direction, toward or away from the singularity, has become time-like. We're not falling through space toward the singularity. We're moving forward in time toward it. Escape is not difficult now. It's not a matter of insufficient fuel or engine power. Escape is geometrically impossible. The structure of space-time itself has changed such that all future-directed paths lead inward. Trying to escape would be like trying to move backward in time. The geometry doesn't allow it. This is genuinely one of the strangest predictions of general relativity, one of the most mind-bending consequences of extreme space-time curvature. We have crossed into a region where the usual distinction between space and time has transformed, where falling toward the singularity and moving forward in time are the same thing. We are inside. We're inside the event horizon now, in a region of space-time that no light, no information, no signal can ever escape from. Everything that happens to us from this moment forward is forever cut off from the outside universe. We could send radio signals, light beams, gravitational wave pulses. All would simply fall inward with us toward the singularity. Nothing propagates outward anymore. The geometry has changed so fundamentally that outward doesn't mean what it used to mean. Looking up, or what we think of as up, toward the direction we came from, we see a shrinking circle of light. The universe we left behind, compressed by extreme space-time curvature into an ever smaller region of the sky. That circle shows us the entire outside cosmos, visible through the event horizon we just crossed. Light from outside can still reach us, can still fall in, even though our light can never escape back out. The view is bizarre. The circle of the outside universe is blue-shifted and time-accelerated. We watch days pass in seconds, then years, then centuries. If we had good enough telescopes, powerful enough instruments, we could watch the sun consume Earth in its red giant phase billions of years from now. We could see the Milky Way and Andromeda galaxies collide and merge. We could watch the far future of the cosmos play out in our remaining minutes. The universe outside is aging at an incomprehensible rate relative to us. This is the flip side of the time dilation. Outside observers see us frozen, our time slowed to near zero. But from our perspective, their time is accelerated, running faster and faster as we fall deeper into the gravitational well. Looking down, toward the singularity, we see darkness. Perhaps, faintly, we can see the glow of other infalling matter, other doomed material that crossed this threshold before us. Ancient stars disrupted by tidal forces, gas clouds, maybe even unfortunate civilizations if any others were foolish enough to approach this close. All of it falls together toward the singularity, all our futures converging to the same inevitable end. The geometry here is profoundly unlike anything that exists in the normal universe. The rules we're used to, the ones that govern space and time outside black holes, the ones our intuition is built on, don't apply here. Down, toward the singularity, isn't really a direction in space anymore. It's a direction in time. The singularity isn't below us or ahead of us in the spatial sense. It's in our future, as inevitable as tomorrow, as unavoidable as aging. We could fire our rocket engines in any direction, toward the singularity, away from it, sideways, any orientation at all, and it wouldn't change our fate. All we'd accomplish is changing our trajectory through this strange space-time, determining the details of how we reach the singularity, not whether we reach it. For a supermassive black hole like this one, we might have minutes before reaching the singularity. The exact time depends on the black hole's mass and our trajectory, but for a 4-million solar mass black hole, an observer falling from rest at the event horizon would reach the singularity in roughly 20 seconds. We're not falling from rest. We cross the horizon with significant velocity, so our time might be even shorter, maybe 10 to 15 seconds from crossing to singularity. For smaller black holes, it would be much faster, microseconds for a stellar mass black hole. For larger ones, longer, minutes or even hours for the most massive supermassive black holes in the universe. But the inevitability is the same. Inside the horizon, the singularity is in everyone's future, and the only question is how long it takes to get there. As we fall deeper, as the distance to the singularity decreases, tidal forces begin to mount. Slowly at first, gently, we start to feel a difference in the gravitational pull between our head and feet. Our feet, being closer to the singularity, assuming we're falling feet first, feel slightly stronger gravity than our head. Outside, in normal space, this tidal effect is negligible. On Earth, the difference in gravitational acceleration between your head and feet is about 1 part in a million, completely imperceptible. But here, inside the event horizon of a black hole, the tidal gradient increases rapidly as we approach the singularity. The difference becomes noticeable, uncomfortable. We feel stretched, like lying on a medieval rack, our body being pulled longer. Simultaneously, we feel compressed from the sides. The geodesics, the paths through space-time that objects follow, converge toward the singularity. This means that objects that start out side by side are pushed together as they fall. We're being stretched vertically and compressed horizontally. This is the beginning of spaghettification, the process that will ultimately disintegrate us completely. The tidal forces grow stronger. What started as uncomfortable becomes painful. Our tissues strain under the stress. Our bones are pulled longer. Our blood vessels distort. At this point, we're still alive, still conscious, still experiencing this consciously. A supermassive black hole affords us this dubious privilege. We get to feel it happening. For a stellar mass black hole, the tidal forces at the event horizon would already be strong enough to tear apart atomic nuclei. We'd be dead before crossing, ripped apart into a stream of individual atoms before we ever reached the point of no return. But here, we survive longer. We cross the horizon intact. We have these precious seconds to experience the inside of a black hole. The tidal forces become overwhelming. We're no longer a coherent human body, but a vertical stream of tissues, being pulled apart like taffy, stretched thinner and thinner. Our cells rupture. Our molecules break apart. Our atoms are being torn away from their neighbors, each following its own individual geodesic toward the singularity. If we could still see, if our eyes haven't been destroyed yet by the tidal forces, we'd watch the circle of the outside universe shrink to a point above us. The universe outside has aged billions of years by now. Whole epochs of cosmic history have played out in our seconds of falling. Stars that didn't exist when we crossed the horizon have been born and died. Galaxies have evolved. The universe has expanded significantly. All of that future compressed into our final moments. But our own time is running out much faster. We're just seconds from the singularity now. The tidal gradient is extreme beyond description. We've been pulled into a thin stream of particles, each atom following its own path, spread out vertically over kilometers, compressed horizontally into a stream just nanometers wide. We're no longer a person. We're no longer even organic matter in any meaningful sense. We're a stream of atoms, then a stream of nuclei and electrons, then perhaps individual quarks as the tidal forces become strong enough to overcome even the strong nuclear force. And ahead of us, unavoidable, inevitable, is the singularity. We've reached the limits of what physics can describe. According to classical general relativity, the singularity is a point of infinite density and infinite curvature, a place where all of the black hole's mass is concentrated into literally zero volume. At the singularity, the tidal forces become infinite. The curvature of spacetime becomes infinite. Every physical quantity we could try to measure diverges to infinity. The equations break down. They return nonsensical answers. General relativity predicts its own failure here, telling us that at the singularity, we've reached the limits of the theory, the boundary beyond which it cannot describe what happens. But what actually happens? What's really there? The truth is, we don't know. Quantum mechanics should become important at such extreme densities and small scales. The singularity, if it's really a mathematical point, would be far smaller than the Planck length, about 10 to the power of negative 35 meters, the scale where quantum effects of gravity should dominate. Maybe quantum effects prevent the formation of a true singularity. Maybe there's quantum pressure, quantum uncertainty, some quantum mechanical effect that halts the collapse before it reaches zero volume. In loop quantum gravity, spacetime itself becomes discrete at the Planck scale, made of tiny atoms of space that can't be subdivided further. In this picture, the collapse might halt at Planck density, creating not a singularity, but a Planck core with enormous but finite density. Maybe there's a quantum bounce. The collapse reverses, and matter rebounds, possibly connecting to another region of spacetime, maybe even creating a new universe on the other side of the black hole. In string theory, the singularity might be replaced by a region of stringy geometry where strings and branes dominate, where the usual notion of points in space breaks down. Or maybe, and this is the most unsettling possibility, maybe the singularity really is a true mathematical singularity, a place where the curvature of spacetime genuinely becomes infinite, where physics as we understand it truly ends. We don't have the theory yet to answer these questions. We don't have a working theory of quantum gravity that can describe what happens when space-time curvature becomes so extreme that quantum effects and gravitational effects are both important. What we do know is this: our journey ends here. The atoms that were once us, the particles that carried the information that defined us, the quantum states that made us who we were, all of that meets the singularity. And then, we don't know. The information about us might be destroyed, violating quantum mechanics' fundamental principles. Or it might be preserved somehow, encoded in subtle quantum correlations, stored on the event horizon, entangled with the Hawking radiation that will eventually be emitted over 10 to the power of 67 years. Or it might tunnel through to another region of space-time, through quantum effects we don't understand. Or the question itself might not make sense because our concept of information breaks down at the singularity. We've reached the ultimate boundary of human knowledge. Beyond this point, we have mathematics that doesn't apply, theories that break down, and questions we can't yet answer. The singularity is where reality, as we understand it, meets its limit. It's the edge of the map, where "Here be dragons" would be written if we were cartographers of space-time. It's the place where the known laws of physics bow out and new physics we haven't discovered yet, must take over. And for us, falling into the singularity, it's the end of the journey. Let's step back from our descent, back from our personal annihilation, and consider the black hole's own future. Because even black holes are not eternal. While we chose a supermassive black hole for our journey, because it allowed us to survive long enough to experience crossing the horizon, stellar mass black holes have something their supermassive cousins lack: a finite, calculable lifespan that's at least theoretically accessible to human comprehension. Through Hawking radiation, all black holes evaporate. All of them. Every single one, from the smallest micro-black holes that might exist to the largest supermassive monsters at the centers of galaxies. All will eventually evaporate completely. For a stellar mass black hole, say, 10 solar masses, a typical remnant of a massive star's death, the evaporation time is approximately 10 to the power of 67 years. Let me put that in perspective. That's 1 followed by 67 zeros. Years. The current age of the universe is about 13.8 billion years, or roughly 10 to the power of 10 years. So a stellar mass black hole will take about 10 to the power of 57 times longer than the current age of the universe to evaporate. That's 10 million trillion 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 trillion. I'm not sure I have enough trillions to adequately express this number, times the current age of the universe. It's a timescale so vast it mocks human comprehension, that makes our entire cosmic history, from the Big Bang to now, seem like the briefest instant, a snap of the fingers, a single frame in an incomprehensibly long movie. For supermassive black holes like Sagittarius A*, the evaporation time is even more absurd, approximately 10 to the power of 100 years or more, depending on the exact mass. 10 to the power of 100 is called a googol, a number so large that if you tried to write it out in decimal notation, you'd run out of atoms in the observable universe before you ran out of zeros. And that's how long it would take for Sagittarius A* to evaporate completely. These timescales are so long that they stretch language and comprehension to their breaking point. We have no meaningful intuition for numbers this large. But here's what's fascinating. Despite these incomprehensible timescales, we can calculate them precisely. We understand the physics well enough. Assuming Hawking's calculations are correct, which we have good theoretical reasons to believe they are, to predict exactly how long each black hole will survive. The evaporation process itself is interesting. As the black hole radiates through Hawking radiation, it loses mass. Very, very slowly at first. A stellar mass black hole loses about 10 to the power of negative 28 watts of power, an absurdly tiny amount, far less than the cosmic microwave background radiation it's absorbing. Currently, all black holes are actually growing, not shrinking, because they absorb more energy from the 2.7 Kelvin cosmic microwave background than they emit through Hawking radiation. Only in the far future, after the universe has expanded and cooled enough that the cosmic microwave background temperature drops below the Hawking temperature of the black hole, will these black holes begin to evaporate. For stellar mass black holes, this happens when the cosmic microwave background cools to below about 60 billionths of a Kelvin, which will take trillions of years as the universe continues to expand. Then, finally, the black holes will start slowly shrinking. And here's the strange thing. As a black hole shrinks, it gets hotter. The Hawking temperature is inversely proportional to mass. Smaller black holes are hotter. So as the black hole evaporates, it heats up. And as it heats up, it radiates faster. The evaporation accelerates. For most of the black hole's lifetime, for 99.999% of those 10 to the power of 67 years, the evaporation is glacially slow, imperceptible. The black hole loses mass atom by atom, particle by particle, in a process so slow that nothing observable happens on human timescales, or geological timescales, or even timescales of stellar evolution. But in the final stages, the evaporation becomes rapid. The last million years of evaporation release more power than the previous trillion years combined. The last second releases more energy than the previous million years. The final moments, the last microseconds, are explosive. The black hole has shrunk to microscopic size, maybe the mass of a mountain compressed to the size of an atomic nucleus, and it's radiating at enormous power. Then, in a final burst, a flash of gamma rays, particles, radiation, the black hole evaporates completely. The event horizon vanishes. The singularity, if it was real, disappears. The black hole simply ceases to exist, its entire mass energy converted into radiation over the incomprehensible span of its lifetime. What's left behind? Radiation. Hawking radiation. Particles spreading outward at the speed of light, carrying away the black hole's energy, and hopefully, if the information paradox has a resolution, the information about everything that ever fell in. But what about tiny black holes, micro-black holes, if they exist? The lifetime formula scales with the cube of the mass, T(m cubed), in appropriate units. A black hole with the mass of Earth would evaporate in about 10 to the power of 50 years. Still incomprehensible, but much shorter than stellar mass black holes. A black hole with the mass of Mount Everest would evaporate in about 1 year. A black hole with the mass of a large ship, maybe 100,000 tons, would evaporate in about a second in a brilliant flash of radiation. A black hole the mass of a human would evaporate in less than a nanosecond. These tiny black holes would be incredibly hot. A human mass black hole would have a Hawking temperature of about 10 to the power of 18 Kelvin, incomprehensibly hot, emitting enormous power in its brief existence before exploding. This was the concern, unfounded, as calculations showed, when the Large Hadron Collider was being built. Could high-energy collisions create micro-black holes? The answer is, almost certainly not, because it would require physics beyond the standard model, extra dimensions with specific properties that probably don't exist. But even if they could, even if every collision created a micro-black hole, they'd evaporate so quickly, existing for far less time than it takes light to cross an atomic nucleus, that they'd be completely harmless, just another decay channel for the collision products. So over unimaginable stretches of time, all black holes evaporate. Let's imagine the far, far future of the universe, trillions upon trillions of years from now. All stars have burned out. The last red dwarfs, the longest-lived stars, exhaust their fuel and fade to black dwarfs, cold stellar remnants radiating only in the infrared and eventually cooling completely. Galaxies have long since stopped forming stars. The universe has expanded so much that distant galaxies are redshifted beyond detection. Each galaxy is alone in an increasingly dark, increasingly cold cosmos. White dwarfs cool. Neutron stars cool. Planets are ejected from their orbits, or fall into stellar remnants through dynamical interactions over trillions of years. Eventually, even protons might decay, though we've never detected this. If they do, on timescales of 10 to the power of 32 years or more, then even white dwarfs and neutron stars would slowly evaporate, their matter decaying into radiation and lighter particles. What would be left? Black holes and radiation. Isolated black holes, the compressed remnants of stars and galaxies, surrounded by an expanding void of increasingly dilute radiation. And then slowly, incomprehensibly slowly, the black holes would evaporate. The smallest ones first, stellar mass black holes taking 10 to the power of 67 years. Then larger ones, black holes formed from galaxy center mergers, taking 10 to the power of 80 or 10 to the power of 90 years. Finally, the supermassive black holes, the 10-billion solar mass monsters that once powered quasars, taking 10 to the power of 100 years, or more to completely evaporate long after all the stars have burned out, long after galaxies have dissolved, long after protons themselves may have decayed. The last black holes will evaporate, releasing their final whispers of radiation into the infinite darkness. And then there will be nothing but photons and neutrinos, spreading apart forever in an ever-expanding, ever-cooling universe approaching absolute zero. This is sometimes called the heat death of the universe, the state of maximum entropy, where no energy gradients remain, where nothing can happen anymore because there's no free energy to make anything happen. The universe becomes a cold, dark, nearly empty void, expanding forever, cooling forever, approaching but never quite reaching absolute zero temperature. Black holes, in this far future scenario, are among the last structures to exist. They're the longest-lasting objects in the universe. They are, in a sense, the universe's tombstones, monuments marking the graves of stars, gathering the cosmos's mass and matter, holding it in their gravitational embrace, maintaining some structure in an increasingly diffuse and entropy-dominated universe. Until finally, they too evaporate, and all structure is gone. This is the ultimate fate of black holes according to our current understanding. Not eternal existence, but slow evaporation over timescales that dwarf cosmic history, eventually releasing everything they ever captured back into the universe as radiation. It's oddly poetic. What goes in must eventually come out, not through the event horizon, which remains a one-way boundary, but through quantum processes at the horizon itself, through the subtle mechanisms of Hawking radiation. Black holes are temporary structures in the cosmic story, just like stars, just like planets, just like galaxies themselves. They last longer than anything else. They outlive everything. But they don't last forever. Nothing does. From John Michel's dark stars to the Event Horizon Telescope images, from 18th century thought experiments to 21st century gravitational wave detectors, our understanding of black holes represents one of humanity's greatest intellectual achievements. Think about what we've accomplished. We predicted black holes with mathematics before we could observe them. Pure thought, pure calculation, following Einstein's equations to their logical conclusions, led us to predict that these impossible objects must exist. We detected them through X-rays from accretion disks, through the orbital mechanics of stars moving around invisible companions, through gravitational waves from their collisions, and finally, through direct imaging of their shadows. Each method independently confirmed what the others suggested. Black holes are real, they are common, and they are fundamental to how the universe works. They've taught us that Einstein was right about gravity, that space-time really is curved by mass and energy, that gravity really is geometry, that the predictions of general relativity hold even in the most extreme conditions we can observe. Every test we've performed, from the precession of Mercury to the gravitational waves from black hole mergers to the shadow of M87*, confirms Einstein's theory. The man was right about the fundamental nature of spacetime. Black holes have shown us that the universe is far stranger than we imagined. They've revealed regions where time runs slow, where space folds in on itself, where the normal rules break down and new physics takes over. They've shown us that information might be fundamentally woven into the fabric of spacetime itself, that our three-dimensional world might be a hologram projected from a two-dimensional surface, that space and time themselves might be emergent rather than fundamental. They've revealed that galaxies and their central black holes grow together, co-evolving over billions of years, shaping each other through a feedback loop we're still working to fully understand. They've shown us that black hole mergers release more power than anything else in the universe. Brief moments where the energy output exceeds all the stars in all the galaxies combined, and that we can detect these events from across the cosmos by listening to spacetime itself. They've demonstrated that the universe's most violent processes, tidal disruptions, quasar accretion, jet launching, are powered by the simplest objects. Black holes defined by just two numbers, mass and spin. Black holes have become tools for studying fundamental physics, for testing Einstein's theory in its most extreme regime, for exploring what happens when quantum mechanics and gravity collide. They've become tools for astronomy, cosmic telescopes through gravitational lensing, markers of galactic history, laboratories for studying accretion physics and jet formation. They've become windows into the quantum nature of gravity, hints toward a theory of quantum gravity that we desperately need but haven't yet found. And we're still discovering. The story is far from over. The Event Horizon Telescope is working on creating movies, not just still images of black holes, showing how matter swirls and jets launch in real time, capturing the dynamics of plasma in the strongest gravitational fields we can observe. They're planning to observe more black holes, build the array out with more telescopes, and achieve even higher resolution. Maybe we'll be able to resolve structure in the accretion disk, see individual clumps of matter spiraling in, watch the base of jets as they're launched. Next-generation gravitational wave detectors will transform our ability to hear the universe. The Einstein Telescope and Cosmic Explorer, planned for the 2030s, will be 10 to 100 times more sensitive than current LIGO. They'll detect stellar mass black hole mergers from across the entire observable universe, seeing these events from when the universe was just hundreds of millions of years old. LISA, launching in the mid-2030s, will open the low-frequency gravitational wave window, detecting supermassive black hole mergers from across cosmic history. We'll hear galaxies colliding, central black holes spiraling together, the cosmic history of structure formation written in gravitational waves. LISA might detect extreme mass ratio in spirals, stellar mass objects spiraling into supermassive black holes over thousands of orbits, mapping the spacetime around supermassive black holes with extraordinary precision, testing general relativity in ways we can't currently imagine. And LISA might even detect primordial gravitational waves from cosmic inflation, carrying information about the universe's first 10 to the power of negative 35 seconds, about physics at energy scales 10 trillion times higher than anything the Large Hadron Collider can achieve. Future missions might use black holes as cosmic telescopes. The photon ring around a black hole's shadow contains an infinite series of nested subrings, each one a higher-order image of the accretion disk, each one carrying information about light that looped around the black hole multiple times before escaping. If we could resolve these subrings, which would require telescope arrays much larger than Earth, maybe stretching to the Moon or to space-based platforms, we could in principle reconstruct the entire sky as seen by the black hole, using it as a cosmic magnifying glass. We might find ways to test the wild ideas that emerged from black hole physics. Does information really escape through Hawking radiation? Can we detect correlations that prove information is preserved? Is the holographic principle real? Is our universe really a hologram? What actually happens at the singularity? Does quantum gravity smooth it out? Do black holes connect to other regions of spacetime? Are wormholes possible, even if not traversable? Can we extract energy from black holes through the Penrose process or other mechanisms? These questions aren't just academic. They're at the frontier of physics, where the next revolution might come from, where new theories will be born. Black holes represent the frontier of human knowledge in the most literal sense. They're where our theories meet their limits, where general relativity and quantum mechanics clash, where new physics must emerge. They remind us that the universe is vast, ancient, complex, and full of wonders we're only beginning to understand. Billions of galaxies, each with a supermassive black hole at its center. Hundreds of millions of stellar mass black holes in our galaxy alone. Mergers happening across the cosmos every few minutes, releasing more energy than we can comprehend, sending gravitational waves rippling through space-time. And they remind us that we, fragile, temporary, impossibly small creatures on a pale blue dot in an average galaxy, can nevertheless reach across billions of light-years and comprehend the incomprehensible. We can photograph the shadow of infinity. We can hear space-time ringing like a bell. We can descend into black holes, if only in our imagination and mathematics, and emerge with understanding. That is extraordinary. That is worth celebrating. We're not just observers of the universe. We're the universe's way of understanding itself, of comprehending its own structure and history, of discovering its own laws. Black holes are nature's way of showing us where physics gets interesting, where reality becomes strange, where new discoveries await. Every black hole we discover, every merger we detect, every image we capture, brings us closer to understanding the cosmos and our place in it. And that journey, that quest for understanding, is what makes us human. We've reached the end of our descent, cosmic travelers. We've fallen from the theoretical musings of 18th century clergymen, through the revolutionary equations of Einstein and Schwarzschild, past the observational triumphs of the 20th and 21st centuries. Cygnus X, 1, Sagittarius A*, the Event Horizon Telescope images, LIGO's gravitational wave detections. We've explored the cosmic menagerie, stellar mass black holes formed from dying stars, supermassive black holes ruling galactic centers, intermediate mass black holes bridging the gap, primordial black holes perhaps lurking as dark matter. We've examined the architecture of these impossible objects, event horizons, singularities, ergospheres, photon spheres, the strange geometry where space and time trade places. We've grappled with the quantum paradoxes, Hawking radiation, information conservation, the holographic principle, the search for quantum gravity. We've witnessed the violence of feeding black holes, accretion disks blazing brighter than billions of suns, jets stretching across millions of light-years, tidal disruptions tearing stars apart, gravitational waves from cosmic collisions. We've heard the universe through LIGO and Virgo, listened to space-time ringing, detected mergers from across the cosmos. We've tested Einstein in the strongest gravitational fields we can observe, watching stars orbit Sagittarius A*, measuring gravitational redshift and orbital precession, confirming again and again that general relativity is correct. And we've descended together through the event horizon and into the singularity, experiencing what no electromagnetic signal can ever report back, witnessing the end of space-time itself. We've explored objects so massive they bend time, so dense they trap light, so extreme they challenge the very foundations of physics. Black holes are more than astronomical objects. They're more than collapsed stars or galactic centers. They're puzzles, challenging us to understand nature at its most extreme. They're laboratories, testing our theories at the boundary of their validity. They're gateways to deeper understanding, pointing toward quantum gravity, toward holography, toward new physics. They're monuments to the universe's creativity, showing us that reality is stranger and more wonderful than we ever imagined. Every black hole we discover, every merger we detect, every image we capture, every theory we test, brings us closer to understanding the cosmos and our place within it. If this journey moved you, if it sparked your curiosity, if it made you see the universe differently, hit that subscribe button right now. Join the Cosmic Drift Chronicles. Become part of our crew of explorers, our community of cosmic wanderers who aren't satisfied with simple answers, who want to dive deep into the universe's greatest mysteries. Because we're just getting started. There are neutron stars to investigate, objects so dense that a teaspoon weighs as much as Mount Everest, where nuclear physics meets general relativity. There are pulsars to explore, cosmic lighthouses spinning hundreds of times per second, more accurate than any human clock. There's dark matter to hunt, the invisible substance that makes up 85% of the matter in the universe, still undetected despite decades of searching. There's dark energy to confront, the mysterious force accelerating the universe's expansion, pushing galaxies apart faster and faster. There are exoplanets to discover, thousands of worlds around other stars, some perhaps harboring life. There are galaxy collisions to witness, the Milky Way and Andromeda on a collision course, set to merge in 4 billion years. There's the cosmic microwave background to decode, the afterglow of the Big Bang, carrying information about the universe's first moments. There are quantum fields to explore, quantum entanglement to understand, the fundamental nature of reality to investigate. Every episode, we're going deeper into the cosmos, unraveling its mysteries together, following the evidence wherever it leads, asking the hardest questions and seeking the truest answers. And I need you with me for the journey. Share this video with someone who loves space, someone who wonders about the universe, someone who asks what if, someone who's ready to fall into the unknown and emerge transformed by understanding. Leave a comment. Tell me which fact surprised you most. What question do you still have? What topic should we drift toward next? What mystery of the cosmos calls to you? Your comments guide where we go next. Your curiosity drives this channel. We're building this together. Until our next journey to the stars, keep looking up. Keep wondering. Keep asking questions. Keep pushing at the boundaries of knowledge. Because somewhere out there, right now, as you watch this, a black hole is forming from a dying star, an event horizon appearing, a singularity creating itself. Two black holes are spiraling together, months away from merger, losing energy to gravitational waves, their fates sealed by geometry. A supermassive black hole is feeding, an accretion disk blazing, jets launching at nearly light speed, visible across the universe. Matter is crossing an event horizon, falling beyond the point of no return, beginning its final journey to the singularity. Stars are orbiting Sagittarius A*, whipping around at thousands of kilometers per second, writing physics experiments across the sky. And somewhere, a gravitational wave is passing through Earth right now, from a merger that happened billions of years ago, compressing and stretching space by less than the width of a proton, carrying information about the universe's most violent events. We're listening, we're watching, we're learning, and we're drifting ever deeper into the cosmic ocean, one discovery at a time. This has been a gentle descent into a black hole. This has been the Cosmic Drift Chronicles. Safe travels, cosmic drifters. Until the stars call us again.